evening and night. We welcome back to our training once again. We hope you are enjoying it, and we ask you to continue persisting with the other. ARA is for get goers. So if you give up easily, then ARA is not going to be for you. But once you climb that steep hill of learning, the benefits are just going to be too enormous for you and for the future generation that will come out of you. So I'd like to start in the morning by thanking our sponsors, Regional University Forum for Capacity Building, that is RUForum, and then the Makerere University Center for Regional Crop Improvement, which is the main founder of this training. I also want to advertise our center, which is offering courses. We have Masters in Plant Breeding and Seed System, which is 2 years. We have PhD in Plant Breeding and Biotechnology, which takes a minimum of 3 years. And then we have also several short courses that is going on. So if you are interested, please, you can visit the website, but you can also send me an email. For those who are doing masters or PhD, if you're already registered in one of the African universities, and then you think you want to do a 6 months research, maybe at Makerere or at the University of Eldoret or the University of Cairo or University of Ghana, well, you can send me an email and then we can discuss, but I will talk about that more tomorrow. So I'd like to welcome you to this day, and then I'm going to hand you over to Susan. So please, we're going to have you're going to get the links for registrations. Please make sure you register. We say at the end of the training, we're going to give out certificates, but also we need your contact so that in case we want to get feedback on the training after a while, because you're going to go and use the knowledge and you see if there's still deficiency. So for us to be able to conduct future trainings, we need you to give feedback. So in case somebody calls you and tells you, talk to you about this course, that will please make sure you give a response. We're not dictating the type of response you give, but please make sure you give a response. Thank you very much. I'm going to take you over to Susan. Let me first get my video and my
All is well. Good morning, participants. I hope you had a good evening and a restful night. We had an assignment. I gave you an exercise to follow the script in R and try to analyze the first data set, which was about soil. So if anybody attempted it, you can put up your hand, and then we can allow you to present. Did anybody attempt the exercise? I would encourage you to start doing work on your own. That's how you learn R. Like, you just dive in, get a fresh script and start doing things by yourself. That's how we learn R. You don't just follow what I have already done, but you can start by writing the line of reading the data in. That is one way of getting confidence in using a software. Do it yourself without looking at somebody's work, and it is going to really help you learn R. So anyone who has put up their hand? Anybody?
Yes, we have already one.
If there's no one, I think
Okay,
we're going to start.
Priska, we have Priska.
Oh, okay. Sorry.
Good morning. Good morning, Prof.
Hello? Yes, I
Yes.
can't hear you.
You can't hear me?
Probably I have to disconnect this. I can't hear you. I don't know whether you can hear me.
I can hear you very well. You can't hear me?
Okay.
You get me?
Huh?
Are you getting me?
I can't hear you, ladies and gentlemen.
Hello.
I think Priska is trying to talk.
Yes.
Yeah, is talking. Helen, maybe
Okay, let me
Susan,
mute
you
myself
increase
and
your
see whether he
volume.
can hear you, Priska.
Okay.
Susan, maybe you increase your volume.
Hello, can you hear me now?
Can you hear me now?
Yes,
I can
we
hear
can
you, but I don't know whether you are getting me.
For my can hear you, Preska. I
You
think
can hear me.
Susan. Yes, Susan has an issue with her headsets, maybe.
I can hear from his computer.
Susan,
Okay, go
thank you.
ahead. I can hear from Thomas's computer.
You
Okay,
can
okay.
hear?
Priska, please go ahead.
Okay. Maybe can I ask whether I can be able to show the way I did it using
Yes,
R?
click share.
Okay. Can you see it?
Yes, just zoom in so that the letters are a bit bigger.
Okay, sorry.
Zoom, go to view.
View.
Go to view on the menu, click view, then zoom.
Zoom in.
Yes.
Okay.
That's okay.
That's okay now?
You can go from the start.
Okay. Now I was using this this library because I had already put in my computer. I had downloaded these packages. So I went to library, all these. So I selected all of them and I ran. So I hope that one is okay. Then I have my data in this path. So I clicked, it is in R training. I clicked that and then it shows me the path. Then I named my data soil. So my data set is soil. So I recalled and it is coming. And there, and now I can see that we have X and Y. So I wanted to look at the structure of that. So I put str, and this is the structure. It is showing me both of them, X and Y, are integers. So I wanted to change the names of X and Y so that I can be able to understand. So I placed these names as a factor which means that in my data, which is soil, I wanted to put soil in phosphorus in soil and P, which stands for phosphorus in plants. And then I rechecked it back on the, then it shows me that in the data frame, there is soil, it has changed, the names have changed. So I use this graph to be able to see how this data will look like in when I draw my graph. So I use the ggplot, and you can see that it is showing that there is a positive linear regression. Then I can say that let me put off this graph first before, let me use this plot so that I can see how the data is moving. Is it the same with the one that I had used before? And for sure, it shows that there is also a positive linear regression. So I can still put off that graph and let me use a different one such that I can be able to see the graph as fast as the equation that it can be able to show me. And here it has already shown the graph, and we can see the equation. Maybe I don't know how this one is being done, so that you can be able to see how it looks like.
Oh, you want to zoom in?
Yes, to show the graph itself when it is.
Go to the graphics section, you see zoom. Click zoom.
Zoom, yes.
Yeah, click. When
This.
you click zoom, then you go and share it. You stop sharing your screen, then you share the graph. Share again.
It is not zooming.
It's not what?
It is not coming to, I'm clicking the zoom, but it is not coming.
Go to share the screen.
Okay.
Then choose the graph.
The graph is not yet coming.
Did you select the graph?
Let me, I'm trying to zoom the graph, but it is not coming out. I don't know why. Should I go to the view?
No, you go back to your screen, share the screen. That you don't need to zoom, it was clear, so you can just use
okay, it is clear, yeah?
Yeah.
Okay, no
so
problem.
You can close the zoom and use the what you have.
Okay.
Okay.
So this is what.
Talk about it.
Yes. Oh, sorry. This is the work that I was working on, and I could see that it has given me the title plus the intercept and the slope, which is shown. And then when I went ahead to look at that intercept in terms of the wordings, then I summarized the work. And it is the same with the one that is being shown in the graph and the ones that is being shown in these coefficients that are it is 61.58, and here it is 62 if you take it if you remove the decimal places and to the highest number.
Okay.
And then when I went to the summary, this is what is giving us. We have the residuals, the minimum, the first quartile, the median, the third quartile, and the maximum, plus the coefficients. We can see that we can still see the slope, the intercept and the slope. You can see the standard error, the t value, and you can see that the p value for this, the intercept versus the phosphorus in soil, significant because we can see it is the number is below our P is below the 0.05, which is the 5%. And we can see that the multiple R regression and the adjusted is significant. So it shows that it is positive, which is about 60. Our F statistics is 12.89. So if you can be able to, if we look at the analysis of variance, that is of phosphorus in plants and versus the one that is in soil. In summary, it can be able to show us the degree of freedom in both the soil, phosphorus in soil versus the residuals. So it shows that there is our N minus 1, which is, we have two factors, which is the phosphorus in soil and phosphorus in plants. So it gives us the numerator as 1 versus the residual, which is N minus 2. So which means that our data, if I can still go back here, it shows that we have two factors. So, and we have 9 objects here, which are being shown. So it means that it is 9 minus 7 minus 2, which is giving us 7. And that is why we are getting this number here. So if we can be able to divide the mean squares of this 1473 divided by 114, then you can be able to get the F value, which is also, it is showing the same, actually with the same one as which we are seen in the coefficients. So I can say that this data that we were given, it shows that the increase in the inorganic phosphorus in soil can also be able to have a higher, there will be an increase in availability of phosphorus in plants by the factor of this 60%. Thank you.
Thank you very much.
Yes.
That was very, very good.
Thank you.
Thank you very much for the good attempt. You can stop sharing, Priska.
Yes.
Is there anybody else who would like to share? We can give one more
Yes, we
person
have
to
Elton.
present.
Elton.
And in case you have a question, put it in the Q&A. My colleague Helen will pick it up and we can always respond to that question.
Elton, you can go ahead. I've promoted
Okay.
Elton. Elton in Doluvu. Unmute yourself. Elton, please unmute yourself.
Okay, thank you, Elton. You can now share your screen.
Since Elton is delaying, Ayo or Lucy, Caroline, go ahead. Caroline, go ahead.
You can share your screen. Okay, can we go ahead? Somebody who is sharing, share your screen.
Caroline, also someone called Simfuke. Caroline or Simfuke, please unmute and share. Simfuke, Caroline, are you?
Anybody? If there is nobody, then we continue with our practicals. Is anybody sharing?
Yes, please continue. They are failed to unmute themselves.
Okay.
In the hospital, we can't continue. Please continue.
Okay, let's continue with our practicals. So, ladies and gentlemen, let's give a clap to Priska for the wonderful work done. And we are going to continue with practicals. And after the practicals, my colleague, Dr. Helen, will come in and do the model building. So I'm going to do multiple regression after this. Okay, so I'm giving you 1 minute. There is new work that has been sent. There's new work that has been sent on the Google link. There are 2 data sets that we need to download, and a script, a short script that we are going to use to show indicator, how do we code, how do we do polynomial regression. So I'm giving you like 3 minutes. Please download that work from the Google link. It's the same Google link. And then let's have the data set and a script. Okay, thank you. Please, Helen, share the Google link again and the registration link for today. Okay. So I'm giving you 1 more minute. Please download the data sets that we need to use. And then let's also go to R. Remember we had learned about simple linear regression, which is a relationship between one response and one independent variable. We also talked about multiple regression, where you have one response and many independent variables. And we said that when you want to do linear regression, the first thing we do is to draw a scatter plot and look at the type of relationship. Is there a linear relationship? Probably the relationship is not linear. So you need to look at the scatter plot. You can also compute the correlation coefficient and find out whether the 2 variables, the response and independent variables, are correlated. Okay. So can I see in the chat? So can we now continue? the Google link has been shared. Can we continue? Okay. Okay. Which link are you talking about? It has been shared. It is right there. Just you can actually click in the link or copy and put it in a Word document, and you click on it, double click, and you get all the folders from day 1 to today. Okay. The materials, the extra materials is in day 6 folder. Okay. Okay, so let's continue. So in R, I assume that everybody is in R. In R, the first thing we do is we load our packages that we are going to use using the library function. So as you see, I'm also going to load all of them. So it will take like a few minutes to finish loading. Okay. And after loading, since he has gone through the simple linear regression, the only thing I want to talk about is the output of linear regression. So we are not going to go through all of them because we had done them. But the first thing we are going to do is to run line 33, which reads in our data. So first of all, let's set the working directorate, which we go to view and session, set working directorate, and choose the directorate. Mine is practice, and there we go. So make sure you set your working directorate to the folder where your data sets are and the code, the R script. Okay. So it said that we do visualization of the data. So we are only going to do one graph. So we will run line 43. Okay. First of all, in the chat, has everybody imported their data? Have you imported your data in R? And put it in a URL. Okay. Copy the link and put it in Google, and you'll be able to get the data sets. Okay, if it's not working. But even if you put it in a Word document and double click on it, using Control, you press Control, then click on the link, it's going to open. Which script are we using? We are using a script called correlation and regression. It is co and regression. That is the script we are using today. Slow download, okay. Okay, so can we continue? Can I see in the chat? What data sets are we using? We are using a data set called EGP production. Check all materials in day 7 folder and download them to your folder. Okay, ladies and gentlemen, can we continue? Can we continue? Have you imported your data in R? I can only see one yes. That is the second one now. I want to see many yeses to show that 400 participants are ready. Okay, so we are going to continue. I'm going to zoom in the screen. Thank you. So zoom in. I think now it's visible. Okay. Okay, so we are going to, once you've brought in your data set of egg P, we are going to construct a scatter plot. It is the descriptive statistics for regression. So once you click on that, you should be seeing a scatter plot. If you don't see the scatter plot, like I don't see mine, then your margins are, it's saying object egg P not found. Okay, let me go and import it also. Probably I didn't do that. So I'm running line 33 and there it is. My data is in. Then I go to line 43, which is used to construct the scatter diagram. And there we are. We can see that the scatter diagram shows that there is a linear relationship between water uptake and food uptake. Okay, so I'm not going to run all those scatter diagrams. What I'm going to go to is the linear model. So we are going to go to line 94. Let's go to line 94 so that we save time. Since Priska went through all those steps, you can, in your free time, go through the same steps. Okay, so we are at line 94. Please make sure you are at line 94. And I'm going to run the linear regression model between uptake, water uptake, and food uptake. And the data is called egg production, egg P. Okay, so when I run line 94 and then I request for R to print the model, it gives me the intercept and the slope. So I want to get all the results, so I use summary in bracket model. So now we have the results. Let me just push it up so that the results are visible. Okay, so the results that we've obtained the estimates, the coefficients of the estimates. The intercept is minus 63.51. The slope is 2.7328. The slope is significant. That analysis shows that we are trying to find out whether there is a linear relationship between water uptake and egg production. That is the hypothesis we are testing. And because now our p-value corresponding to food uptake is 0.000 something, you can see it is 4.02 times 10 to the power minus 8. It is smaller than 0.05. We have evidence to reject the null hypothesis. The null hypothesis states that there is no linear relationship. And the alternative says that there is a linear relationship between food uptake and water uptake. So because now it is smaller than 0.05, we have evidence to reject the null and conclude that there is a significant linear relationship between water uptake and food uptake. So after that, we want to look at these estimates and write a linear regression model. So our model is going to be water uptake equals minus 63.51 plus 2.733 food uptake. How do we interpret those values? For the slope, for every extra gram of food taken in, the increase in water uptake, the birds, increase the amount of water taken in by 2.73 milliliters. So every time you give the bird 1 more gram of food, they are going to take more water. The increment in water taken is 2.733 milliliter. The intercept is negative. It says that when you don't give the birds food, it is the value of y when food uptake is 0. When there is no food, the birds are not taking in water. Does it make sense? Doesn't make sense biologically. because the birds actually take in water even when they've not eaten food. So that's why I said that sometimes the negative intercept doesn't really make sense biologically. Statistically, we would say that that is the amount of water that would be taken in when the birds are not taking in food. So what does negative mean in terms of water uptake? That one we need to investigate and find out how do we put the negative intercept to use when we are looking at the biology side of it. So that is our equation, and we can now predict the amount of water that can be taken in by the birds given a particular amount of food. When we are doing prediction, we do not predict beyond the data set that was used to formulate the model. So if you look at our summary, we can do summary statistics and look at the minimum and the maximum value of y and x. So when we are doing our predictions, the minimum and maximum value of x, that is the range within which we can do our prediction. Beyond that range, we don't know the relationship between water uptake and food uptake. That's why we don't predict beyond the range of the data set. The other thing we want to look at is the R multiple R squared. That is the coefficient of determination. It is 0.956, which we can change to percentage and becomes 95.6%, indicating that the amount of variability explained in water uptake by regressing on to food uptake is 95.6%. That is the variability explained, which is a lot of variability. Now, from there, we want to look at the analysis of variance table. So if we want to look at the analysis of variance table, we run the model 2. So go to line 98 and run that line, and then run the summary statistics. So again, I am going to just extend the script up and so that the console is widened, and we are interested in the analysis of variance table. So the analysis of variance table gives us the degrees of freedom corresponding to food uptake and residuals, and the total degrees of freedom is 10 plus 1, which is 11. So those are the total number of observations. Oh no, 10 plus 2, which is 12. The total number of observations in the data set is 12. Remember, residual degrees of freedom, the formula is n minus p. And we have two parameters, the intercept and the slope. So for us to get the total number of observation, it should be 10 plus 2, which gives us 12 total degrees of freedom, total number of observations. Now, I wanted us to look at the degrees of freedom for food uptake. We say the formula is the number of parameters in the model minus 1. We have the intercept and the slope. There are 2. Minus 1, we get 1 degree of freedom. And then the residual degrees of freedom is n minus p. Since the number of parameters are 2, we are going to have 12 minus 2, giving us 10. So the overall p-value, you can see it is similar to the p-value corresponding to food uptake. It is testing the same hypothesis that there's no linear relationship between food uptake and water, and then the alternative is that there is a linear relationship between water uptake and food uptake. Okay, similar interpretation. So with that, you can either use the coefficient table to interpret or make conclusions about your hypothesis, or you can use the analysis of variance under regression. Okay, so from there, we are going to look at the last part, which is the residuals. Okay, we are only going to look at the residuals, And under residuals, you use the model where you've run your regression. So I'm just running line 146 again to make sure that my model 2 is still active. Then I'm using the function par mflow to specify that I want my window for the graphics to have 2 graphs per row. So I run that and then run the plot. We are plotting the information in the model. It has the residue. And remember, why are we running this particular one? Is to test the assumption of normality and homogeneity of residues. And if those assumptions are valid, then we are good to go. Our model is okay. So let us plot. And in case you get a red figure, is saying the figure's margin is too large. So I am going to reduce my figure margin and then run it again, run the plot command. It's still complaining, so I'm going to use the view. You go to view and zoom out and also zoom out. So then I've made so then I run my line 159 and it gives us the residual plots. So I'm going to zoom in the residual plots and share them. So there we are. I hope they are visible, those residual plots. And we can see that the first plot is testing the assumption of homogeneity, meaning that the variance is constant, the variance of the residuals, and we can see it's a random scatter of points. There's no particular pattern. Even R has tried to draw a line in it, and it is just showing us it's a random scatter of points, indicating that the residuals have constant variance. Then the normal QQ plot is testing for normality of residuals. And once the points fall on that dotted line, then the residuals are normally distributed. Okay. Okay, so let's go ahead and the next line, I'm going to stop sharing. And the next line talks about you can use a test to find out whether your data is normally distributed. And that is the spheral test, which is line 152. So we can run that and we are testing the model. And in the model, we are looking for residuals. So when we run that, we get an output here down in the console. And the output is saying that the p-value, the hypothesis you're testing is that the data is normally distributed. That is the null. The alternative says the data is not normally distributed. The significance level you're looking at is alpha of 0.05. Now, our p-value is way bigger than 0.05, meaning that there is a lot of evidence, a strong evidence not to reject the null hypothesis and conclude that our residuals are normally distributed. So that's how we test normality of residuals. You can even test the response. Instead of putting residuals, you put in the name of the response, water uptake. Okay, so that is simple linear regression. We want to look at multiple regression. And in the chat, should I continue? Or can you send us today's registration link? My colleagues will send it out. Okay, it is already sent. Okay, please go ahead. Thank you. Okay, let's go to multiple regression. Okay, so in multiple regression, we are still going to use the same data set, and I want to construct a scatter plot to see whether there's actually a linear relationship between the very many variables that I have. My response is water uptake. The other variables are independent variable, have food uptake and and egg production. Okay, so I'm running this window, mfro, using the power function to also specify that I want to have many graphs. Now, because I have already a graph in the window, what I'm going to do is I'm going to type graphic off. When you type graphic off and run, it erases the graph in the plot window. So now after that, we can now run our power function and then run the plot function. So you can see that we have so many plots. I think even if I don't zoom, you're able to see those plots. Are you able to see the plots in the chart? Are you able to see the plots? Okay. Okay, great. If you look in the bottom right corner, the plots are there. So you can see that the first column is for water uptake. The second column of graphs is food uptake. The third one is egg production. Now, water uptake, the second graph is a graph between water uptake and food uptake. It shows a linear relationship. The third graph is a relationship between water uptake and egg production. There is a relationship, but it is a little bit weak. Then we can have food uptake and egg production. There is also another relationship, but it is also a bit weak. Okay, so that's to see whether there is a linear relationship before you run your model. Okay, so now we run model 3, which is a multiple regression between water uptake, food, and egg production. So run line 162, and then let's run the summary, and let's look at the output. So when you look at the console, we see that it has given us coefficients, and we have the intercept, we have the slope for food uptake, and the slope for egg production. So we can see that the hypothesis we are testing is that there is no linear relationship between water uptake, food, and egg production. Alternative is that there is a linear relationship between water uptake, food, and egg production. So if we look at the p-value, the column for p-value, that corresponds to food, we see that the p-value is smaller than 0.05, and we have the evidence to reject the null, conclude that there is a strong linear relationship between water uptake and food. Then when we go to egg production, we find that the p-value is 0.333. It is greater than 0.05, meaning that we have no evidence to reject the null. There is no significant linear relationship between water uptake and egg production. We can look at the R squared. It is 0.96 and convert it to percentage, meaning 96% of the variation has been explained by the regression between water uptake, food, and egg production. But remember that we say that we should consider R squared adjust, because R squared adjust is not affected by adding parameters in the model. It does not increase, but it adjusts for any parameter added in the model. So in that case, our R squared adjust is 0.95, which is 95.2% of the variability has been explained in water uptake. So we can go ahead. Now we see that egg production, there is no significant relationship, but biologically, are birds affected if they don't take water? Does egg production drop or increase if the birds do not take water? I think water is very necessary when making eggs. So that you look at the biology behind egg production. I believe that those people doing agriculture, especially animal production, should be knowing that water is very important for digesting food and then making the eggs. We also need water. So even if it's non-significant, we might leave it in the model for biological purposes. You only eliminate a variable if biologically it's not important. So after getting the numbers, you have to add on the biology. Look at the system. Do we need egg production in the system? Okay. Does it influence water? Its slope indicates that for every egg produced, there is a decrease in water taken because it's negative. So there we need to look at the biology before we can eliminate egg production from the model. But we are going to look at model building. So you will see how and when we eliminate a variable. Okay, so let's go and see what we have. So the next line is we can add a coefficient to we can produce coefficients for our confidence interval for our coefficients. That is the slope, the intercept for both the intercept and the two slopes. So you use that command conf intercept. So if you run, you will see that you've produced intercepts, the lower and the upper value of food uptake and egg production. Okay? Sometimes when you're running regression, they want to put, you are requested to put a confidence band on your model. So you can use the same line to put a confidence band on your model. Then you can run, if you don't want to write the whole model the way you see it, you can abbreviate and use dot, comma. Water uptake is a function of dot, comma, data equals egg P, and you get the same results. So if we run that and run the summary, we see that we are getting. So those are alternative ways of dealing with R. And then the same way we did with the residues, you can actually go back and plot residues. So if we just say plot PR mfro C into -2, then we run that just to specify that we want our, then we say that we want to plot in bracket model 4. Then if we run, we get the residual plots. Okay, so then the interpretation is still the same. We are looking at homogeneity, we are looking at normality of residues. So that is it for multiple and simple linear regression. I want us to change. We are going to open a new script. Unless if you have a question, you can put it in the Q&A, or you can put it in the chat if it's very short. Unless if you have a problem, I want us to shift and look at indicator variables, and then also look at polynomial regression briefly, so that I can give time for model building and also for categorical data analysis. So I am going to type graph off so that this goes off, graphics off, then I run, and I'll do Control L to clear my console so it is clear. Then for the environment, there is a longer command which I have not really tried to put in my head, but it is right there. Okay, so I want you to turn in the script, in the chat. Can I continue? Why do we run correlation analysis, and why do we run correlation analysis? Okay, we can continue. Remember we talked about correlation. We can run correlation analysis as a descriptive way to find out whether the variables are correlated. Okay, so in here you can actually go to the correlation function. We remember we had that in our EDA, that's why I didn't actually bring it here, but you can go to the scripts that we had and run our correlation. Okay, so I want us to shift to a script called regextra. I just put this for you to have a feel of when do we use the dummy variables, okay? Just that short thing. We have only very short script called regextra. Please, giving you 1 minute, open regextra and also download dataset called uptake and another one called HUD. Now, a small history about the dataset. The experiment I was looking at uptake of iron, and he had concentration. So he had a certain concentration and was looking at how the plants uptake rubidium and bromide. So those one are the two categories that we have in our data set. And about hardwood concentration, when we are making paper, the machine crushes the wood and forms a concentration called pulp. Then that concentration plus addition of chemicals, it is fed into a machine to make paper. So that data set for polynomial regression is about hardwood concentration and the strength of paper. So the strength is varied, the concentration is varied until we get the required strength of paper, and that is the data set that I have for polynomial regression. So in the chart, can we continue? Do you all have the data set? Where is the data? In a folder, day 7, isn't it? Day 7, please, can you send the link again? They are saying no. Day 7, go to day 7 and get the script. Okay, so the link is going to be sent with no data. No. Is it true that there's no data in day 7? The data set is there. Somebody says it's the data is there in day 7, and somebody is saying no reg extra. Is it true? Can you check the script? That it is there, please. No, the script is there. We do not have the script. No script. Can you upload the script, please? It's going to be uploaded. Share the link, yes. Helen says it's going to share the script in the chat itself, so please stop sending. If you upload, okay, send the link and also share the script in the chat. The script name is regextra.r, but you pick it from the chat or go to the Google link. It has updated information. Share the registration form. Please, Helen, share the registration form. I'm lost. I don't know where you got lost from, but you can let us know. We will pick you up. Matthias, why are you lost? What is the best time to test assumption? After formulating the model, you test the assumptions. Okay, the Google link has been sent. It has day 7 data. It has day 7 data. Okay, so 1 minute, one more minute. There is no reg. Can you pick it from the chat, please? And Helen, update day 7. And if it fails, if the assumptions fail, then you do either log transformation, or you go and try and model the distribution of the data set. Somebody says it's there. Answer the questions in the Q&A. Okay, sorry about that. How do I get the graph to show? Increase your margins, okay, using view, zoom out. If the data is not normally distributed, then you do log transformation, natural log transformation of the response and the dependent variable. Oh, margin is too large, go to view and zoom out. Then the margins would decrease and make the plot window bigger. Based on the residual, can we say that the data is normally distributed? Yes, the data was normally distributed. Some clarification about spheral test. We say the p-value was bigger than 0.05. The hypothesis we are testing is that the data is normally distributed versus the alternative that the data is not normally distributed. Now, because the p-value was bigger than 0.05, meaning that the chance to reject the null has become higher, so we have no evidence to reject the null, conclude that the data is normally distributed. What is the best time to test the assumption after you've formulated the model? If that is the case, no, why do we run correlation analysis and when to run regression analysis? Correlation analysis is run at the beginning before you run your regression. At the end, I need teaching material. Yes, it has been posted in the Google chat. I'm in the Q&A. Please explain the command lm. lm is linear model. The command lm is linear model, and it says mod is the object where the model is going to be stored. Then lm is linear model, is the function that tells R to do a regression analysis. Uptake is your response. That squiggle you see, it says it's a function of time and iron. Please, what is a confidence band? Those are the upper and lower limit of either the slope or intercept. What does the significance value in, that was for soil, pH, cannot change working directorate, data frame, cannot open connection. That one Helen will help. Can you explain the residual plots? That one I did. I think I have, how do we perform multicollinearity test? We use the VI, variance inflation factor, for testing multicollinearity, and that one I'll leave it for you to do it. Prof, what does, okay. Okay, the rest I've answered. Explain about F statistic. The F statistic value can also be used to test the hypothesis. Okay? Now, when you have an F table, you can look at your residual degrees of freedom, which is the denominator, and the numerator is the regression degrees of freedom. Pick a value that intersects those two at 5% in the F table, and then you get that value, compare it with the calculated value. If the tabulated value is less than the calculated value, then we have evidence to reject the null. If the calculated value, if the tabulated value from the table is smaller than the one from R, then you reject the null. If it is bigger than the one from R, we do not reject the null. Okay. So now, since you've had enough time to upload, can I continue in the chat? I want to see in the chat whether you have the data. The data sets are two. One is called uptake, another one is called hard, and the script is called reg extra. So I can see in the chat, continue, great. The what? Huh? I what? The R script is called reg extra.r. Okay, so let's, since you've already loaded and we have not closed the packages, I don't think there's going to be a problem us not running the packages. Let's just read the data in. So click line number 1, which says uptake assign read.csv in bracket double quotes uptake.csv. Okay, so let's read in the data and click uptake. So you can see in the console we have our data, and it consists of 3 variables, 10 observations. It has time, uptake, and iron. Iron is our categorical variable with 2 levels. Okay, I want us to pay attention. The next line, line 4, we want to create a new variable by assigning codes onto rubidium and bromide, our categorical variable. So we use the line uptake $iron1. We are creating a new variable called iron1. We assign if else uptake $iron is equal to rubidium, then it is named this or 1. Sorry, let me repeat. We formulated a new variable called iron1, and we are saying if iron is called rubidium, then it is called 0. Else it will be 1. That is the code there you see. Rubidium, 0, 1. So if it is rubidium, it is called 0, and else it will be 1. So let's run line number 4 and run view uptake, and we see that in the RStudio window, we'll see uptake, time, iron, and a new variable called iron1, which has 000 for rubidium and 11 for bromide. So we formulated our dummy variable. We said yesterday the number of dummy variable is equal to the number of levels of the categorical variable minus 1. So we needed only 1 dummy variable. Okay? Are we together there? Let me see in the chat. Should I continue? Can I continue in the chat? Okay, I'm going to continue. No, please recap. Pardon. Please repeat. Okay, I'm going to repeat. So I'm closing this uptake, and I'm going to go back to the window where I've written the script. So we've read in our data uptake, and uptake consists of a categorical variable called iron with the two levels, rubidium and bromide. We want to assign codes to rubidium and bromide. And what we do, we write our code uptake $iron2, iron1 is the new variable, and we want to assign 0 or 1. So we use the if else function, uptake, call iron. If it is rubidium, call it 0, or else call it 1. Then when you run that and then view your uptake, it brings up the data set. The data set uptake in your script, after you've run, have you got a data set called, which has 4 variables now with 10 observation, where iron1 is the new variable? So we can call it a dummy variable, but I've called it iron1. So in the chat, have you gotten the new data set? Do you have the new data set? Yes. Okay. I can see some no's, and I don't know why you have no. Can you go to Q&A? Object uptake, where is uptake data? Now, did you download the data set? Cannot find uptake data. Do you have, go to the Google link, please, and go to day 7. That's what we've been talking about, and get the data set. If you don't get the data set, we can't proceed. Please, can we get the data set? Have some gotten the data set? Do you all have the data set called uptake? There is the Google link. Check in day 7. Yes, where you have the data set. Some people have the data set. So if you've not gotten the data set, then you've not clicked at the link. And if you have the script, then you should also have the data set. Download day 7 again. That's what they are saying. Send the link, Google link. Esther has sent the Google link. Please, let's do that very fast because time is against us. Unless if you don't want us to share more information. Priska is saying scroll down in day 7 and find uptake. Those who are using those who don't have data set are using yesterday's folder. It has been updated. Please click the Google link again and upload the data called uptake. That's why I gave you 4 minutes to do that. So I'm giving you 1 minute. 1 minute. Extract the data so that we can continue. Kindly maximize the window, okay? Let me increase the window. I think that is good. Should I continue? Okay. I'm going to continue. Most of the people have the data set. And let's continue. Okay, I'm going to redo. Okay, good. They've gotten the data set. Okay, let me continue. I've said that the line number 4 helps us to code our data, which has the categorical variable. And we create a new variable called iron1 in our data set uptake. That's why we've written uptake $iron1. And we use a function if else to tell R to create a categorical variable. To create a new variable called iron1 and pick iron. Wherever there is rubidium, call it 0. If else, call it 1. If it's not rubidium, call it 1. So when you run that line and view your data, you will get a data set with 4 variables and 10 observations. Hopefully that is clear now. Okay, now we want to plot our data set and find out whether there is a linear relationship or no. So there is line 7 talks about the names. Why do you bring the names out? So that you write the correct names in your script. That's why we have call names uptake. So we see that we have 4 variables, including iron1. Now, when you plot uptake as a function of time, we get a graph. So can you see the graph in the plot window? Is it visible? Can I see in the chart? Do I need to zoom out? Yes, okay, the graph is visible. So if we look at this graph, in the chart, can we fit only one model? Okay, it's visible. Can we fit only one model to the data? One line? If we look at that graph, Julia says no. Because if we fit one line, it is going to go in between the data set and all the observations are going to be off the line. Okay? So the next thing we are going to do, since you see that there are two groups, one belonging to bromide and another one belonging to rubidium, we are going to include the variable iron 1 in our data set, in our model. Okay? And see whether we need actually to have different lines. So the next line, line number 9, the object is called mode, and we assign a linear model. Uptake is a function of time plus iron 1. Data is called uptake. So run that and run the summary. And let's look at the console. When we look at the console, let's go to the coefficients. When we look at time, the p-value is small, smaller than 0.05. We have evidence to reject the null and conclude there is a linear relationship between uptake and time. When we look at iron, it also shows us that the p-value is small, indicating there is a linear relationship between uptake and iron. Now, this dummy variable you've included in your data set, it is actually specifying that we need different intercepts for our two iron, bromide and rubidium. Okay? So you can see that in the chart, we have two lines, parallel lines, different intercept, similar slope. So after getting these values, we can actually take those values. What I'm going to do is I'm going to copy this particular part and take it to a Word document, and we write the model. Copy, go to Word. I'm going to share the Word document in a minute. Okay. Okay, so I'm going to stop sharing and share the Word document. Remember yesterday we said that once you get your analysis, you write your models. Okay? So what we are going to do here is to write our model. So remember the general model is the intercept is 2.777. The slope for time is 0.181. And the slope for iron is minus 5.28. But remember we said if rubidium is in a under iron variable, it is called 0. And if else, that means if you find bromide, name it 1. So let's go up here. So the equation, I hope it is visible, equation for rubidium. Okay? The general equation, I'm going to write general equation is that uptake is equal to 2.77. Sorry about that. 2.77 plus 0.181 time, then plus minus 5.28 iron. Okay? So that is our general model. Now for rubidium, we said rubidium is equal to 0. Isn't that what we said in our command? Rubidium is equal to 0. Okay? So in this model, wherever we see iron, we substitute with 0. So then it's going to be equal to 2.77 plus 0.181 time. And if we multiply minus 5.28 by 0, we get 0, isn't it? Okay, so our new equation is uptake is equal to 2.77 plus 0.181. So that is our new equation for rubidium. Let's go to the equation for bromide, where bromide was named 1. Okay, the general equation, we have it here. So we are going to substitute wherever you see iron, substitute with 1, and 1 times minus 5.28 becomes 5.28. So our new equation is going to be uptake is equal to 2.77 plus 0.181 time minus 5.28. Okay, so then put like terms together. 2.77 is a number and minus 5.77 is a number. So our model is going to be uptake is equal to minus, we can say 2.77 minus 5.28 plus 0.181. So in that case, what do we get when we subtract? Can somebody tell us 2.77 minus in the chat? I'm in the chat. Anybody? Okay, minus 2.5. Great. Okay, so minus, so uptake is equal to minus 2. Somebody 503. Okay, then plus 0.181 time. Okay, so this is the model for rubidium. I will put it in red and bold. And the model for uptake, okay, I'll put it in black and bold. So in the chart, is that clear? Can we go to polynomial regression? So that is your final output. The major part is to come up with models so that now you can predict for rubidium. You can now also predict for bromide. Okay, so that is when you have a categorical variable and you want to run regression. So I'm going to stop sharing this part and then go to polynomial. Somebody is saying, please, 5.28 iron. 5.2 is the slope for iron, but remember iron is a categorical variable where bromide is 1 and then rubidium is 0. So wherever there is iron, we substitute with either 0 to get an equation for rubidium. So if we multiply 5.28 times 0, we get 0. That's why we come up with the bold model for rubidium. Now for uptake, iron was specified as 1, and then we have our uptake like that. What happens when you have 3 levels? We talked about it yesterday, but now you'll end up with the 2 dummy variables and then run all those dummy variables in your data set, and you'll be able to write your models. Okay? Okay. Let me go to, I'm going to stop sharing and share the script. We go to polynomial regression And once we finish polynomial, I'm going to clean my console and okay. I have this data set. Please read in data set called hard. It is about hardwood concentration. I got this data set from a textbook called Montgomery and Parker. This data set is about hardwood, as I've told you. So we use the read.csv function to read our data. I'm just going to click on that and view the data set. So if you look at the console, you will see that it has hardwood concentration and tensile strength. Okay, and it has 19 observations. Now the first thing I'm going to do is to plot our data set. So let's run line 16. When you run line 16, you get something very interesting. So in the chart, what do you observe in the plot? Can I see in the chart what you observe in the plot? If you've run in the chart, what do you observe in the plot? I don't see any comment. Why build a model? Okay, let me check. Yeah, curvilinear relationship, loading hard, okay, quadratic, okay, great, increasing, then decreasing. Can we fit a linear model to the data? Can I see some suggestion? Diminishing return. Okay, can we fit a linear model? No, we can't fit a linear model. So that is the importance of constructing a scatter diagram. You're able to know whether now you should fit a linear model or not. Okay, thank you very much. Let's now go to the script again. I do not have the script. You pick it from the Google link. Okay, thank you very much. Let's run, assuming that even if you've plotted and you see it is not linear, let's still run the linear regression. That is line 18, we run the linear regression. And let's get the output. So once you run the linear regression, we want to look at the console and see what the console has given us. So in the console, we see that we have an intercept and a slope corresponding to hardwood concentration. It shows that it is significant. There is a linear relationship between tensile strength and hardwood concentration of paper. Now, when we look at the console, multiple R squared, it is 0.3054. That is very low, meaning that we've not explained approximately 60% of the variation in tensile strength. And that also tells us the linear model is not good for the data, since it is only explaining 30%. So what we are going to do there is to model the way we see the data, add a quadratic model onto it. So let's go to the script. Let's go. Before we run the script, I want us also to look at the residuals and see what happens when you run a wrong model. Okay, so I have this function pow, and I'm just telling R I want my 2 by 2 graphics, and then run the plots. Okay, it says I have very big margins, so let me try to reduce them and run again. It's still complaining, so I'll go to view and reduce the margin, view, zoom out, and view, zoom out. Okay, so I'm going to run the model again. Is it still complaining? Okay, there we are. I'm going to zoom this time. I want us to see and share. I want to share that particular graph so that you see what is happening when you run a wrong model. This is what you see when you run a wrong model. You can see that it is R is already telling you that actually the linear model is not suitable for your data. It is showing a curvilinear regression. Yeah. If you see residuals versus fitted value plot, the first plot on top left corner, you will see that the residuals are increasing with the fitted values, meaning there is heterogeneity of variance, or the variance is not constant. And also the linear model is not suitable for our data, because you see the red line there, it's not a linear model, it is a curvilinear model. And when we go to our QQ plot, our data set is not normally distributed. You can see that it is skewed. The points are running away from the dotted line. Most of the points are running away from the dotted line. So once you see that, let's go and fit a quadratic model and see what happens. So I'm going to stop sharing this and share the R script. And the next script is, the second line is about, let me increase the font, zoom in. Okay, so line 25 is where we are going to run our quadratic regression. And what we do, we formulate a new variable called hardwood concentration 2, where we are squaring hardwood. So that is the line 25. So in here we are saying we want in hardwood, you select hardwood concentration and then square it. You can see we've assigned that sign there, which is like an inverted V squared. So if we run that line 25 and view the data, you will see that you've formulated a third variable called concentration 2. That is where you've squared hardwood concentration. You're introducing a quadratic variable. Okay, so I'm going to, after that, let's run the model including the new variable. So mod 2 is the object which has the linear model with hardwood concentration squared. We also leave in hardwood concentration because there's no way you can have a quadratic equation without the linear part of it. So let's run that bit and summary. And let's look at in the chat. Are we all okay? Please, I want all materials link. You will get it. Okay, yes. Okay, there is a Google link coming up. We are all okay. Okay. So let's look at the console and interpret the output. After that, we look at the residual plots and see how they've improved. Okay, so in the console, now we have the intercept. Hardwood concentration, the linear part is significant, and the quadratic part is also significant. So there is a significant quadratic relationship between tensile strength and hardwood concentration. Now, when we look at R squared adjust, or even if you look at R squared only, the R squared has totally improved from 0.3 to 0.9, from 30% to 90%. And R squared adjust, which I told you we can use in multiple regression, is 0.89.7, which is approximately 90%. So 90% of the variation has been explained in tensile strength by regressing a quadratic model onto that response. Okay? So we now see that the quadratic equation is suitable for this data. Let's now look at the residual plots to see how they've improved. That is the last part of this presentation. And we are just going to run our, again, our par function and then our plot model. So we have new graphs, which I'm going to share in a minute. We have new graphs from the quadratic model. You can see that the first plot, residuals versus fitted value, it is showing that now we have a random scatter of points. The residuals are no longer increasing with fitted values. It is just a random scatter, only that R has fitted the quadratic equation onto the data set. When you look at the normal probability plot, it has greatly improved. Now most of the dotted line values, most of the dots, those dots you see are falling on this line here. And I think you can see that there has been a great improvement when you fit the correct model. So that is polynomial regression. Any question? I'm going to stop sharing this in the chat or Q&A. Any question before I pen off? Can you perform polynomial regression for more than one predictor? Yes. If yes, how do you select the best combination? That is model building coming up. So Nicholas, we are going to do model building. You will see how to select variables to select the best predictor. Even if there are 4, you'll be able to select the best predictor. Explain residuals versus leverage. Residuals versus leverage, I didn't really pay attention to it, and it is just telling us that when you plot residuals versus the leverage, you're also getting a random scatter of points showing that there's constant variance, but I didn't really pay attention to that. Assumptions for polynomial regression are similar to linear regression. And the reason for squaring, hardwood concentration, not tensile strength, because it is actually hardwood which is making which is bringing in the quadratic relationship, not tensile strength. Okay, so if you want to find out whether it is tensile strength, then you have to change and regress tensile strength versus hardwood, where hardwood is the y variable and tensile is the x, to find out whether you should be squaring tensile. But in this case, we see clearly that there has been an improvement in our model, showing that we've done the right thing. Okay, in Q&A, let me see. Okay, I think I've answered all these ones. Thank you so much. Please practice. After this, don't just keep the notes or the R script, keep practicing. Thank you, participants. Squaring is not actually trying to normalize the data. We are trying to fit a quadratic model. We are modeling actually how the data looks. Okay? But no, when you fit the correct model, even the residuals will be normally distributed. Okay, so I'm handing over to Lady Helen. Pardon? Do you need a break? Or we continue? Do you need a break, ladies and gentlemen? They say yes, they need a break. So yes, 10 minutes. Okay, so you will come back at 11:50. Okay. Okay, so they are saying too early to have a break. Some are saying no. Okay. Okay, now let's continue if you don't need a break. It's too early. Helen will give you a break. So Helen is going to talk about model building. And after model building, she'll be talking about categorical data analysis. Break is midday. Okay, thank you. So I hand over.
A very good morning, still morning in Uganda. I hope that you had the best during Professor Suzanne's presentation. Okay. Yes, in Uganda, it's still morning, depending on where you are. Good afternoon, good evening, and so on. Welcome to the next presentation. I just want to confirm in the chat if you can hear me well, and then I proceed. Okay. Okay, great. Now, we are going to use materials still from day 7. It's the same folder where we're going to use the model building PowerPoint. Then we'll move on to R, which is a building and categorical data.R. And then we'll use the work salaries.csv. Okay, now let's start. Let me share the slides. So you're going to look at model building. Everything emanates from what Prof has just discussed about regression. People are asking question, how can you get the best model? The point is that each work that you do or different data sets call for different regression analysis. But the point is we need to get a model that is simpler and can easily be generalized to the rest of the data. So let's move on and see what happens. So the point is that within model building, okay, in this case, you've got very many regressors. The regressors, I mean the explanatory variables, some of them call them predictor variables, or you can call them independent variables, okay? They are very many. And you are wondering, among these many, what subset can you come up with? Or of the 20, maybe which ones should I opt for such that they give me the best model that I can use for my data. So finding the appropriate subset of regression for the model is very important. And this is called variable selection problem. And it's basically what I'm going to be discussing. So there are various methods that can be used to select the regressors that you need, or call them the independent variables that you want to check on how they influence your response variables. And all these methods, as we're going to see during the building, they're referred to as the stepwise type procedures. Okay. So what is the aim of model building? The point is that remember, you go to the field, you collect different data, and most of the time that the data that we collect is always different from from your colleague and so on. So the point is that we need to determine a model that is simple, but yet it's the best fit for the data that you've collected. That is the aim of model building. You could be, for example, having like maybe, let's say you've got 10 variables, that 10 independent variables that influence a dependent variable. But of these many 10, you might find that you don't need all of them. You just need a few that are very important to predict your data, to predict what you want to come up with. So it is the relevancy of model building. And so even the other aim why we do model building is that we want to get only the variables that are significant to avoid the risk of overfitting the model that we are going to use. So you've just looked at how an equation, how a linear regression or a multiple regression looks like. So in case we take this particular example, like if my outcome variable is growth, and it is being influenced by rainfall, soil type, variety, sunlight, and fertilizer. All these other variables on my right-hand side, we refer to them as the independent variables, call them explanatory, call them predictor variables. And then what I have on this particular side of Y on my left, that is my Y, it is my dependent variable. So we are trying to see how do these variables on the right-hand side influence growth. So you can write it in this particular case, which I guess is what you've been seeing throughout from what Susan has been discussing. All right, so we need to understand when do we add and when do we delete variables, because sometimes you can you might want to test, for example, in case you're considering a simple linear regression whereby you're only having one, you're trying to check how one independent variable influences your outcome variable, okay? And you see that, yes, it is significant, and you want to add another independent variable. But all you need to understand is that, you know, to test whether you want to add another variable to the model that already has another variable, you need to check if there is a statistical significance. Sometimes in case you put the first variable and your P is significant, then it implies that you can continue with that variable. However, in case you add another dependent variable and then the first variable you added becomes insignificant, then it implies that you can delete it out, because now this time around the p-value is non-significant. Most of the time we can either use an f-test or a p-value. All those criteria can support you on when to delete and when to add and when to delete. All right, so like we discussed earlier, that the f-test is based on determination of the amount of reduction in the error sums of What about there? Can you hear me? Yes. Okay, great. Sorry about that. So let's continue. I was still talking about the things that you can consider in case you want to either add or delete a variable that you want to include or exclude from your model. All right, so we want to still, like I mentioned earlier, that the P criteria can also be used to determine whether it is advantageous to add one or more independent variables to a multiple regression model. So most of the time you can decide either if you want to use an F statistics or you want to use the p-value, and all this can be compared to the level of significance, that is alpha. Okay. However, yes, I know sometimes it's very difficult to determine the p-values, but what we see that most of the different packages or different softwares can be used to determine to help you determine the p-value, and then from there you can decide whether to add or delete a variable, like what we've been doing, what you've been doing in linear regression, whereby you're able to determine that basing on the output from R, this variable is significant and then the other is not. So it's the same thing that we are going to use. All right, so now let's move on and look at the different variable selection procedures that we can use to support us determine the model that we can use or that can be used to fit our model. So among the variable selection procedures, we have the stepwise regression, we have forward selection, or call it forward addition, we have backward elimination, or you can call it backward deletion. So in all this, they are iterative in nature, as we are going to, these all these particular procedures. And when it comes to when we are trying to analyze which one is, how do we add in the independent variables, we always, when it comes to forward selection, we add one independent variable at a time. And when it comes to backward elimination or backward deletion, we delete one variable at a time. And it's interesting that R does it automatically. Yes, it keeps, if it's forward, it keeps adding and then adding one variable at a time automatically, and then with backward elimination, it deletes one variable at a time. But the point is, we are going to base our discussion on the p-values and see what can we add, what can we subtract. And then we also have the best subsets regression. In this particular case, different subsets of independent variables are evaluated. For example, in case you're having, let's say you're having 3 independent variables, it implies that you can create the subsets you're talking about, that you can create different regression models within using one of the different independent variables that you're having. And so in that particular case, they will act as your regression models. But you find that when you look at it deeply, it's more complex, and it's a little complex because you're going to come up with many regression models, and by the end of the day, you'll fail to understand which one should I pick out and which one should I not pick out. Okay, now let's move on and start on with the stepwise selection procedures. Like I mentioned, there are 3 of them. We have got forward selection, backward selection, and then stepwise selection. So what happens, let's start with the forward selection. The way you hear the term forward. So how do we start? So this one begins with assumption that there is no regressor in the model other than the intercept. Usually when you're writing out a regression model, in case there is no intercept, then there is no slope. If you're not adding any explanatory variable or any independent variable, usually your y is equal to c. That y is equal to c, which c is the intercept. So we first assume that we are not adding any regressor. And in case we run that model and we get that alpha is the criteria we're going to use, that our alpha is less than 0.05, then it implies that now we can move on and add another regressor or another independent variable. So that is step number 1. And then number 2, remember what we said, that in this particular case, an independent variable, only one variable is added at a time. Okay, for example here, like I said, the regressor are inserted in the model one at a time. So in case I've got my y equal to beta, which is my intercept, now I start adding one dependent variable, in this case, which is the soil type. When I run my model and I see that the p-value is less than 0.05, then that gives me more gas to tell me that yes, even soil type is a significant variable that I need to have in my regression model. All right, but then after that, in case the first regressor selected will be one with the first regressor that will be selected will be the one with the largest correlation with the responses. Remember, we are having very many regressors or explanatory variables. Maybe you can have 4 of them. So when the software is picking, what it will do, it will pick the one that has got the largest correlation with the response variable. In this particular case, if I'm referring to the example, the one of growth. So if the p is less than 0.5, then it implies that that variable will stay in. Then I continue to see what if now, remember it is forward. I started with non-variable, the intercept, I added 1, now I want to add another one. What happens? Okay, so these are the steps that I was talking about. So the first regressor is entered. In case we see that it's less than 0.05, we continue. All right, now the second regressor entered is the one with the largest correlation with the response variable after adjusting the effect of the first one. Remember, we keep adding variables. So this same story keeps on and on. provided all these variables that are being catered in the model, they have got the p-value that is less than 0.05, or depending on the level of significance that you've set. Maybe somebody would say that I'm setting it to 0.1 or 1% level of significance. But the good thing is that the statistical package does it automatically. But the point is that we need to understand what is behind, what does the computer do, such that we're able to make a refined decision. Okay, that is for the case of forward selection. In summary, for forward selection, the things that you can keep at your fingertips. Number one, as we are trying to set within your data set, you've got various independent variables, and you want to see how the various independent variables influence your outcome variable. Okay, as you start to build the model, you start with a model where you don't have any regressor or you don't have any explanatory variable. You start with the intercept. In case it is significant, as you run it in your statistical package, in this case R, then you can go ahead and add another variable. Like I mentioned, the one that will be added on that particular model, it will be the one with the highest correlation than the rest. And then the same story will happen to the next variable you add, and so on. All the ones that will be having the p-value, which is greater than 0.05, they will not be added. Okay, and so it applies up to when you get to the nth variable. So that is the backward selection. Let me ask in the chat, is that okay? Are we on the same page? Okay, great. Now let's move on to the second, when we've gotten backward, and then we are going to say, how do we do it in R? All right, now when you come to the backward selection procedure, now in this particular case, it is the opposite of forward selection. Okay, what backward selection does, it includes all your variables, all your independent variables within the model. If you've gotten 6 independent variables, it's going to first consider all of them. It's the first model that you're going to have with all the variables, and then later, what happens is that then one variable is dropped at a time, basing on the criteria that alpha is less than 0.05. So whatever, in case there is an independent variable that has got a p-value which is greater than 0.05, then it will be deleted one at a time. So with R, it is being done automatically, as we are going to see the moment we put the commands, what happens. And then later at the end, it will be able to give you a model that best suits your data, what you want to use, which is simple and appropriate for the kind of data that you have. So, and then, like I said, with the backward selection, it will terminate when all the other variables that are there that have got the alpha, when the alpha is not less than 0.05, it will terminate, and then it will give you the output. So the point is that in case maybe we had 4 variables, or let's say 8 variables, your first model will have all of them, and then later in the background, the variables that will be having your alpha to be greater than 0.05, they will be dropped out one by one. And in this particular case, once a variable is dropped out, it is not brought back. Yet so you should have that in mind. So once the variable is out and it has been dropped, it stays out. It cannot be recalled again. All right. And so with R, it will be able to tell you, well, among the 8, maybe 3 or 4 variables are the ones that suits the criteria, and they've got the alphas as less than 0.05. So they're the ones that you can use to best describe the data you're using. Okay, we are going to go through a very simple example that is by Thomas Southwestern, and see practically what happens in the background as you're using R. How do you go about in case you're considering backward selection? Because sometimes you might say, like, you want to first consider a full model with the backward elimination, you want to consider a full model, and then later you start narrowing down to the variables that you want to consider. So this is the example. It says that Tom Zamora, a real estate investor, has just moved to Clarksville and wants to learn about the city's residential real estate market. Okay, Tom has randomly selected 25 house for sale listing from the Sunday newspaper and collect the data partially listed on an upcoming slide. Okay, so this is what we are having. And so the question is that we want to develop using the backward elimination procedure and then a multiple regression model to predict the sale price of the houses in this particular state. So now this is just a part of the data that we are having. Among the variables that we have the segment of the city. They are northern, northwest, southern, northeastern, etc. Another variable, it is selling price. It's in USDs. Then the house size, the number of bedrooms. If we have 4, 2, this one is also categorical, the number of bathroom that the house has, and then the garage size. Okay, maybe in case somebody has a car, whether the house has a garage or the house doesn't, or it has 2, or it has 3, among others. So this is how our data set looks like. We want to see how our dependent variable in this particular case is the selling price. Okay, and how do these other factors, for example, the segment of the city where the house is, the house size, the number of bedrooms, the number of bathroom, and the garage size influence the selling price of the house. So let's check, how are we going to get our best model when in case we're using backward elimination? Okay, this is what happens. So what we do, we fit a multiple linear regression model. Okay, we are fitting a multiple regression model with and in this case, we are considering all our variables. We have all our independent variables, the segment of the city, the house size, the number of bedrooms, the number of bathrooms, and the garage size. Okay, so when we fit them, we are going to do this in R. What happened is that in case we fit, we have the household size, the bedroom, the bathroom, and then the car. This is a regression output. We've got the coefficients, we've got the standard error, the test statistics, and then the p-value. Like I mentioned, the one that will have what the program does, it deletes out one variable at a time, and it deletes out the one that has got the greatest p-value, because our interest is to have a p-values that are less than 0.05. So in this particular case, what is going to happen, looking at the variables that we have considered, cars has got the biggest p-value. So in this particular case, we are going to drop it, or it's the one that is going to first be removed. And then you continue, you rerun again, you redo the process again. If you redo the process again, in this particular case, the garage size, so in this case is the independent variable with the highest p-value of 0.697, which is greater than 0.5. 0.05. Since we are doing backward elimination, so this car variable or the garage size is going to be removed, and we are not going to put it back again. So what happens after dropping the garage size, we refit again a multiple regression on the remaining variables and see what happens next. So now when we move on, still we get the output from R, as we are going to see. Among the, we're having the house size, the bedroom, and then the bathroom. We see that the bedroom size, the p-value is 0.28113, the greatest of the 3 that we are having. Since it has got a greater p-value, which is of 0.28113, remember with backward, we eliminate one variable at a time. So also that one will be dropped. Okay, so the bedroom, in this particular case, is the independent variable with the highest p-value, which is of 0.281, and this p-value is greater than 0.05. So we are going to drop it. it is removed from the model and automatically, and it is deleted and we don't call it back. So now we run the multiple regression now on the remaining variables. Remember, I'm showing you what happens, what the computer does, such that by the end of the day, you can quickly link this particular information to what we are going to see in R. Okay, now still when we fit a regression model, a multiple regression on the remaining variables. Now in this particular case, we have the house size and then the bedroom size. And when you look here, we are having the one with the greatest p-value is the bathrooms with 0.10974. So it implies that still even this variable can be deleted out because according to the criteria, the p-value is greater than 0.05. So we are going to remove bathroom, and we are going to, only variable that's going to be remaining is the house size. So looking at this, the bathroom is the independent variable with the highest p-value of 0.110, and it's greater than 0.05. So we remove it, and then what happens is we run again the multiple regression, and it is performed again on the remaining independent variable and see, is it significant or it is not. So in case we do that, you find that with it was only the house size that remained, and for it it's giving us 8.7e to the power 0.9, which is this value is less than 0.05. So it implies that now in this particular case, it is only one independent variable, the house size, that influences the price of the house. So like I mentioned, the house size is the only independent variable remaining in the model. And since it is significant, so now we rewrite our final model based from what we are having. We are having the intercept and then also our intercept, rewriting it out, it's minus 9.8669, then plus 11.3383 to come up with using the coefficients now to write out our regression model. So now this is the final, this is the estimated regression equation we are coming up with using backward selection or backward deletion. And so the point is that among the different variables we had, all the variables were not significant, but of the many, of the 6 that we had, it is only one variable that can easily fit on the data that was collected, and it's a house size. So from here, in case you know the house size, you can be able to fit it where there is house size and be able to get the selling price of that particular house. So that is how backward elimination works. Let me stop and ask in the chat if you're on the same page. Is it okay? Can I continue? All right. So far, so good. Okay. Remember, with the backward selection, we drop one variable at a time, one independent variable at a time. With the forward, we add one variable at a time. Okay, and with the backward, the moment a variable is deleted, it is not recalled back. It is gone. We continue with the ones that have remained. Now let's move on to the stepwise regression. When it comes to the stepwise regression, this one combines both. It combines both the forward and the backward selection process. So there are two criteria involved. The point is that, for example, we are going to start with the forward, okay? In case you've got an intercept that is significant, and then you add in an independent variable, and then still your p-value becomes, your p-value is significant or less than 0.05. But then as you move on maybe to add in another value, and you find that when you add in another value, then it makes the first variable insignificant. Remember, it is forward and back. Then the first one is dropped out, and then the second variable is left there. So in case we are taking this particular example, it's like you can enter and it gives you an alpha, which is 0.05, okay? and then you keep that variable. But in case you add in another variable, and then the first variable you added in becomes insignificant, then automatically the program will drop it out. So it is a leverage of two, the forward and then the backward selection process. All right. And then in this particular case, in case a variable is dropped at one point, it can be called back in case it makes the model significant. So in case a variable is dropped, it can still be brought back at a certain point as you're checking if it fits the criteria. Yet it's not the case when it comes to the backward. So let's take this example. I've got y, which is equal to my intercept beta naught plus the rainfall. I'm starting with the forward selection process. And then in case I can add rain, in case my beta is significant, I start by adding one variable, okay? If it is significant also, I go on and add another variable. In this particular case, in case I add soil type. However, in case I add soil type, and rainfall becomes insignificant, then it implies that this one will be dropped and I'll stay with only the soil type. But in case this one stays significant and soil type is not significant, then it will be dropped. And so the process goes on like that until when I come up with until when I get the model that I want. So in this particular case, variables included in the model are assessed in both ways, either with forward or with backward. And the variables removed at one point be re-entered at a later step. That is very important because it can be taken up. So the rules are set for the variables to enter the model and to be removed from the model statistics. So, however, we have to note that none of the methods result into the best regressors. The point is that how can we get an accurate or the best model, particularly to the data that in case, well, you might fit a forward, you fit a backward, and then you fit a stepwise. Hmm? Why? I'm using okay, let me ask in the chat. Can you hear me now? No, could it be its internet or? Hmm? But I'm using internet for this place. A second. Okay, let me share and then I'll repeat. Okay, let me ask again in the chat. Can you hear me now? Am I clear? I'm going to be more loud and say such that it could be it's an internet. Okay, I'm going to increase my voice. Okay, let me repeat a little bit and we continue. All right, I'd discuss backward and I think it's okay. Now, let me discuss again stepwise regression. Okay, when we come to stepwise regression, for it combines both forward and backward selection. If you've understood how forward works and how backward works, then it implies that for stepwise regression, we are going to consider it combines both processes. It combines both the forward and then the backward. Remember the criteria of how do we include our variables. We want to include variables that influence the outcome variable. So, and the criteria is you can either use an F statistics, or we can use alpha, the p-values, all right? So in case you're having, the criteria is in case your alpha is less than 0.5, okay, you can, you consider the variable. If it is greater than 0.5, you remove the variable. So in this particular case, as we are starting the stepwise regression, we start with the forward. Remember what forward does. You start with only an intercept, whereby you've not put any variable. If that intercept gives you, is significant, you continue, add another variable. Like in this particular case, I've added rainfall. It's just an hypothetical example, but we're going to apply it on the data set and see how it works. Okay, in case I add rainfall, I'm trying to see how rainfall influences Y. For example, in case my Y is growth of a plant. All right, so if my p-value that I get on rainfall, it is less than 0.05, then it implies that I consider rainfall variable as significant. However, in case I add in another variable, for example, in this particular case, if I add soil type in my equation, in case I run that regression, and it happens that this time around, soil type is the one that is significant and rainfall it's not. So what the program will do, it will now drop because it is forward and backward. Yes, I included in rainfall before, but on the second, when I added in another variable soil type, rainfall became insignificant. So it implies that rainfall will be removed. I'll remove rainfall. However, as I keep adding in more variables, and at one point, in case the rainfall becomes significant, then it implies that it can be recalled back and I put it in my what? In my model. So the point is I can add a variable if it's significant, but at one point in case it becomes insignificant, it is deleted out. You work forth and then backwards. Okay, there are some questions, alpha to enter and then alpha to remove. Okay, the point is that we want to find a regression model that best fits the data that we have. And remember, we always have different data sets, or you go out to collect data differently from the other. And the model that might work for my data might not work for your data, but you want to choose a regression model that fits best your data. And in case you're having many variables, you want to pick the variables that are significant to your data set. So we use a criteria. If you remember what Professor Susan was discussing, saying that there is a relationship between the independent variable and the dependent variable when the p is less than 0.05. In other words, that's when you reject the null hypothesis, that's when you reject H naught. When your p-value, when you find that it's less than 0.05 and you go in with for the alternative. So I'm just building on what she discussed. So as you add, in case you're having a variable, I'm talking about the independent variable, in case you're adding it in the model, okay, in a regression model, and you see that the factor, and you see that its p-value is greater than 0.05. So in that particular case, it implies that it doesn't suit the criteria, so it has to be dropped. So there is adding and dropping. When alpha is greater than 0.05, automatically the program will delete it out. The moment the alpha of that independent variable is less than 0.05, it will be retained. So that's what I'm talking about, the alpha enter and then the alpha remove. What are we removing? We are adding the dependent variable and we are removing the independent variables. So you either add or remove. You're trying to say among the different independent variables that you have in your data set, how do they, among them, which of the many, for example, which of the 8 really influence your dependent variable? That is the enter and the remove, okay? But everything emanates on what is your p-value, what is your alpha? Is it less than 0.05? That is the criteria that we are using. And then the other question is that, yes, what will happen if the intercept is not significant? Like we've been discussing earlier, most of the time, these intercepts per se, they might not make sense as you're pushing on. Sometimes you have to push on and see, in case I add an independent variable to make a simple linear regression model and see, does it make sense, or does my p-value greater than 0.05 or it is less than 0.05? So because we are deleting out the independent variable, so that is where your main focus should be. You have to, so the point is that you have to continue and see how the different independent variables that you want to consider in your model influence your response variable. How are you factoring in the segment of CT in the regression? The point is, when it comes to backward elimination, okay, consider all the variables. You consider a full model. So in this full model, you put in all the variables, and the computer will keep, the process is, it is iterative. The computer will keep on dropping one variable at a time, provided it is greater than 0.05. That is the criteria, and that is the rhythm that we are going to be using. Okay. And then when we come to the stepwise regression, now it combines both. It combines the forward and then the backward. Remember, with the forward, you start with only an intercept when there is no regression, no regressor. Okay, then you start adding one variable at a time. And then it's also quite interesting that when it comes to forward selection, like I mentioned, it adds the one that has got the highest correlation with the response variable among the rest of the other independent variables. And most of the time when that variable is added and it's significant, it will keep into the regression. When we come to then you keep adding in, you keep adding. Forward, we are adding. With backward, we are minusing. But with the stepwise regression, this one combines the two, the forward and then the backward selection process. So what happens, it starts with the forward. It starts when there is no variable, okay? Then it keeps adding one. That is for the case of the forward. If it is significant, it is retained. In case you add another variable, okay, a second independent variable, and this second variable makes the first variable insignificant, because it also involves the backward process, it will delete it out and retain the second variable. But remember, variables in this case that are dropped out can be recalled back at a later age in case they make the model significant. Okay, let me move on to the next slide, then I'll get to the chart. Okay. There is a question that how is training data and testing data related to model development? I mean, when it comes to training data, you're doing cross-validation. You're trying to tell the program, is you can do it in the program, that maybe consider 80% of my data as training data and then 20% as my testing data. So by the end of the day, you first do the model development with the training data, and then you test it and see whether it works the same way on the testing data, period. That is how it works. All right, let's move on. So I said that variables included in the model are assessed in both ways, that is considering the forward and then the backward. And variables removed at one step could be re-entered at a later step. The same rule works. We are considering when our P is less than 0.05. Okay, let me ask in the chat that can you now differentiate between the three selection procedures? Can anyone share the training materials for today? Can you now differentiate between the three? Okay. Very well. Great. Oh. Okay, now let's move on. We are going to look at methods for evaluating the subset regression model. So we want to say, yes, you can try and fit all these. You can try and fit all these regression procedures. You can use the forward, you can use the backward, you can use the stepwise. But by the end of the day, you still want to understand among the three, which one should I take, such that I use it for the data that I have, and it can give me the best results that I'm looking for. So we are going to look at methods for evaluating subset regression models. Okay, so there are things that we need to consider. So what we are going to do, we'll choose one with the largest R squared adjusted. Professor Susan has been mentioning about this throughout when we started the regression analysis. So when you feed these particular three models, we are going to select the one with the largest R squared adjusted. Remember from what she was explaining that what R squared does, for it tries to adjust as you keep on adding different independent variables in the model, it tries to adjust them. So it is always better that we use the one with the largest, the one with the largest R squared. Okay, it's a model that we shall choose. We can as well look at the mean square error, the one that will have the smallest. We are going to see how do we calculate that in R. And then we can also consider the AIC, that is the archaic information criteria. We always take the one that the smallest, it is the best one. However, you can also look at the MAR-CP. In this case, this one must be equal to the number of parameters used in the model. What do I mean by parameters? For example, in case your regression model has got 4 variables, okay? So your CP, the CP that you're going to consider will be equal to 5. It implies that you're going to have the 4 variables, that is with then plus the one intercept, okay? Remember an intercept and then plus the slopes that you're going to have. So a good model has a CP, the MAR-CP equal to K plus 1, whereby my 1 is the intercept and then K are the what? Are the variables that I'm considering. Okay, so it must be equal to the number of parameters. So as you check, depending on the CP that you get, as R can give you this, depending on what you're getting, then you relate back to the data that you have. Is it equal to the number of parameters that I'm considering in my model? In case you're considering your model, which is having, for example, 3 variables, then it implies that in your CP should be equal to 4, considering the 3 slopes plus the intercept. That is the point behind. And also, BIC. But we are not looking at that. Okay, let's go on. We have also the prediction sum of squares. Sometimes it is denoted as press. Also, depending on the 3 models, you can choose the one with the smallest. The smaller the press value, the better the model's predictive ability. So, so the point is, whatever that we are going to look at, you can, when you want, among your 3 models, you need to look at your R adjusted, your R squared adjusted. You can use the AIC, the one with the smallest is the best one. You can consider the Maro CP. That one, does the value you get equal the number of parameters you're using the model? Like I gave an example, in case of 4 variables, then your CP should be 5. The 4 variables plus the intercept, then you come up with 5. And then also you can consider the press, implying that if it is smaller, then you'll be able to come up with a model that gives you the greatest predictability of your data. So those are the things that we are going to consider on the different models. This is the same thing that I've just explained, that when you're using an adjusted R squared, choose a model with the highest values. And this has been already talked about. So the point is, okay, what is the appropriate model? So after all the above steps, okay, you need to choose the best model. You can even create a small table, okay? And then you can create a small table and you put in AIC, you put in R adjusted, you put CP, and then you also put press. So after this, you can write in the columns, reg 1, maybe for the backward, reg 2 for the forward, and then reg 3 for the one of stepwise. And then you start listing out these different variables that you get. And then after that, you can choose and determine which one will suit your, will choose your, will fit your data. AIC, that is the archaic information criteria. Then the BIC is the Bayesian information criteria. I say that the CP, that is the Maro CP, it helps us to determine the number of parameters in the model that we are having. So when we are choosing the appropriate, we are not looking at BIC in this particular case, because we are trying to get a model that gives us the smallest MSA, that is the mean square error. So we also want the one that gives us the smallest AIC. These are the criteria that we are going to consider. Of course, when you move on to other statistical methods, like in case you want to do time series analysis, that's when you can use, for example, the BIC, also at the same time the AIC, in case you want to determine the optimal lag. At the back of your mind, what you should note in mind is that what exactly are you doing? In case I want to do multiple regression analysis, then what exactly do I need? Because yes, there are many information criteria out there, but specifically to the analysis that you want to see, which one should you choose and opt for? So the point is, after choosing the appropriate model of the 3, you can go ahead and test the regression assumptions and see if the assumptions are not violated. And after that, you can proceed and do the analysis of the model and be able now to do the regression like Professor Susan was discussing. Okay, let me ask in the chat. Are we on the same page? Is that mandatory to put on the table with the more relevant? Well, I'm saying that because it will be easy for you to tell. I mean, if you put it in a table, it will be easy for you to tell that, well, basing on this is better than the other. And then it just helps you to quickly come up with the best model, the appropriate model that suits your data. It is just a suggestion that I've made, because when you put them in table form, you can quickly compare and say, oh, well, if I look at, for example, the reg for the backward, then I can consider the AIC is small, or the R adjusted is small compared to the one with forward, or compared to the one with backward selection. And then you can select out the one that suits the evaluation methods that we have considered. So is that okay? Can I continue? Or you're tired? Can we go on? AIC is archaic information criteria. We take a break up to, let me check, 15. Okay, up to a time? Okay, let's take a short break. for 10 minutes, and then we come back at 12:50. So after the moment you get back, we move on to R and see how does it work. And in that particular case, we'll be using the building and categorical data.R script. Okay, let's take a break. 12:50 Ugandan time. So convert it to your time zone. Okay. Hello everyone. Was worried. Loud silence. Okay. We are back from the break. I think we can continue. Can you hear me? Okay, great. So now what we are going to do, when we are breaking off, I say that when we get back, let's try to move to R and see how this works. So go to folder D7 and open your building and categorical data.R script. It's what we are going to use, and it's in D7. So check in the Google link and download the D7 folder, and then put it on your computer, and we'll start from there. So I'm going to share my R. I did. Okay. All right. Let's continue. So what I'm going to, we are using the data set worksalaries.csv. And this is the same data set we used on day one. So it's the same data set that we are going to use. What is changing is the script. So please kindly also check and confirm that you have everything in one folder. I'm going to share the script I'm talking about, such that everyone gets to see it's what we are going to use. Okay, with the worksalaries.csv dataset that we are going to use, it is the one here. We've got rank, we have discipline, we have years since service. Yes, we have years since PhD, we have years in service, the sex, and then the salary. So this is the data set that we are going to be using, and check. We are going to build 3 regression models, and then we choose which one is the best that we can go in for to suit this data very well. So I'm going to stop sharing, and then now I share my R script. In the D7 folder, kindly pick building and categorical data.R. So can I check in the chat? Have you opened your R datasets now? Are we on the same page? So such that we start. Okay, fine. So now, like we mentioned earlier in the beginning, that we always keep building different libraries that you want to use. And most of the time, the moment they are installed, then all you need to do is just to load the libraries. The moment they are loaded, you don't need to install anything again. So what I'm going to do, which I also want you to do that side, set a working directory to the folder where you've got the worksalaries.csv data. It's what, import it in R. So it's what I'm doing at line 13. This is my working directory where my data is, and I want to read my data worksalaries.csv. So when I read it, I can check in the environment, and I see it is telling me that I've got 397 observations and 6 variables. I told you that in case you want to view your data in R, you can click on this icon. The moment you click on it, you'll be able to see, it will display automatically here. And just you want to confirm and see, is what I have in the Excel, is what I've imported the same to what looks similar to what I want. All right, remember still in this same data set, I mentioned earlier that we've got some categorical variables, because when you run the structure, in your structure, they are telling you, yes, it's a data frame, fine, with 397 observations and 6 variables. However, rank, we are looking at the rank of professors. We have the associate, the assistant, and then the professor, but it's being read as a character. And then we also have sex, which we need to also adjust and also discipline. We have A and B, the humanities and then the sciences. So we need to tell R that please read these as categorical variables. I'm glad that at least now we all know these particular steps. So it's what I'm going to do. We just use the as factor command. I believe we're on the same page. Maybe, let me hope I'm not rushing. Are we on the same page? Have you done with importing the data? Please type in the chat. Okay. Yes, great. So as I work out, also try to do the same on your computer. Let's run, the moment you've set your working directorate right, then the rest, then you should, and loaded the right libraries, then the rest should be okay. So let's move on. Now we are moving on to variable selection procedures. I don't know if I need to zoom my, if I zoom in or you're able to see the write-ups. Are you able to see the commands on my slide? I continue. Okay. Okay, fine. So we are going to start with backward selection. Remember with the backward selection, what we said, we fit the model at a go, and then later the R will automatically delete out, will consider the moment the p-value is less than 0.5, that variable will be retained. In case it's greater, it will be dropped. It drops one at a time. But let's first fit our multiple regression model. So by now, I understand we are well versed with the LM command. And then inside here, we put our dependent variable, and then it's a function. The moment you can put dot, the moment you put dot, you're telling R that include all the variables, all the independent variables that within my data set, consider them. So instead of writing one by one, sometimes, for example, you can have many independent variables. So instead of you writing one at a go, you can say salary tilde dot. Dot means that all the other variables within the model. And then my data set is salary. So I'm trying to define my model with all the predictors. And I'm labeling it. I'm using my object as fit all. Like we've been talking about what an object is. So you can change it to anything that you want. So in case I run this data set, okay, I come and ask summary of my object, summary of fit all. So you can check that you've been looking at a multiple regression with Professor Susan, and this is the output that you've been coming up with. Okay, in case you fit a multiple regression, implying that you can put in more than one independent, one independent variable. So basically, this is the one with we first start with a multiple regression. But remember now, as we move on, yes, you can see what is happening, that some of the p-values are less than 0.5, others are not. But basically, having a typical look on the few variables that we are considering, looking at your p-values, the ones that are less than 0.05. So now what we are going to do, we are going to proceed and see what happens in the selection. But this was just the full model, whereby we considered all the independent variables. We are trying to see how do other variables influence salary, right? So this is the same thing. You can as well write formula fit all. You'll still come up with similar results. But I'm not going to run that because you can try to practice it in your own free time. It's the same results that I'm going to get. So what I do, I come to this step is very important. What happens, remember, you can use the help command in case you need more help. So what happens is that I use the command step, okay? Inside step, what I first fit in is my model, fit all, okay? I've got my regression model, fit all, and then my data set is salaries. Now, what is good here, you command R because everything is automatic. You tell R that what direction do I want? I want to use a backward selection procedure. What is going to happen is that R will compute everything and drop all the variables that it will think that it has got p-values that are greater than 0.05. So in case I feed in what I want, and now so in case I move on, I'll tell R that no, this time around I don't want backward, I want a forward, or I will put both, implying that it will give me both the one of the stepwise. So if I run that command and I want to show the output. So in case I run this particular command, step fit all my data set, and then the direction is backward. What is happening is that it is telling me, it is bringing the equation salaries as a function of rank, discipline, years since PhD, and then plus, and so on. So it is telling me in this particular case that when the first AIC, the archaic information criteria that is giving me, it is 7965.19. And when I look at my result, it is telling me that, remember with backward, we are minusing. So it is minusing 6, implying that my 6 had a p-value. The moment you see a minus, if you look at this particular side, we are seeing minuses. So for it, it's minusing 6. And it is saying that in case you minus 6, then your AIC will reduce from 7965.19, and then it will reduce to 7964.8. Remember, we are looking at a model that will give us the lowest AIC. Okay. And then when you move on further, there is now it is bringing none. It implies that you cannot take up, it cannot drop more values, because none is like a stopping criteria. Because when you look at the AIC, in case you proceed ahead, then it implies that our AIC will increase now. Instead of 7964.8, now see there is an increment of 7963.2. So when you look at this, what should come at the back of your mind, that the moment you come to none, that is the stopping part, that don't need to in case you don't need to minus other variables apart from 6. So the point where, as you move further, you see that when you minus 6, now your AIC, this AIC that you're seeing here, it is the one that I'm having at this particular point. Okay, this was 7964.8, which is the same thing as here if you round it off. So what for it does, now it concludes that none did not go any further. So it stopped with this particular formula, that the factors that influence salary, in case you're considering backward selection, we are having rank, we are having discipline, years of service, and then the years since PhD. Okay, it further goes on to tell you the different coefficients, okay, for the multiple regression. So because it showed us none, we did not move further. That was the stopping criterion, that we don't need to move, we are not going to reduce any other variable apart from 6 that reduce our AIC. So now at this particular point, what we have to note is our AIC, because it's one of the things that we are going to read as we want to determine whether it will give us the appropriate model. So I ran this line, and this is the explanation I'm having. Okay, now you can also from here, from my step, I can come here and create an object. I can create an object, and I say that I'm going to call the whole of this particular line, and I give it an object as back AIC. Okay, I can still run this. It is still going to be the same thing. When I run that from the object, I'm getting similar information. I'm just changing goalposts, but it's the same thing. So it is my AI is 7965.19, and it's still telling me you need to remove sex. If you remove sex, and then you cannot proceed anymore. In this particular case, it's none. So my AIC is being reduced from 7965.19 to 7964.8. All right. Now, if that was in case it removes sex, then now when you look at this second equation now, sex is not had sex in the first equation. So in the second one, sex has been dropped because of the p-value was greater than 0.05. And we remained in our second equation with the rank, discipline, years since PhD, and then years of service. And after that, it doesn't continue anymore. Like I mentioned, R does it automatically. It's about you have to scroll down once and see which is the last equation that we are given. So in this, because there is a none, we cannot proceed. Therefore, as we are writing out our regression, the multiple regression, it's going to be the variables we are going to consider in this particular case that will influence salary. We have rank, the discipline, the years since PhD, and then the years in service. All right, let's see. Basing on this particular object, I can extract out my AIC. By using the command extract AIC, the archaic information criteria of this object. So when I run this one, what it does, it returns my AI, it returns the CP and then the AIC. All right. So here, what we are having is the AIC, which we've already seen here. It is 7964.75. So it is what I'm having. So like I mentioned, you can create a table and then you write for backward, my AIC is 7964.75. And then you record your CP as 6. Okay, so in this particular case, remember the number of variables plus the intercept. Here, how many variables am I considering? I have 1, 2, 3, 4, 5, plus my intercept, which is giving me 6. So my CP is 6. So you can as well extract out the coefficients in case you want to use them. And then you go ahead and look at your adjusted R squared. And this is the command that we are using. Summary, my object. And then from here, I'm saying that the $sign give me the adjusted R squared. When I run that, and it is giving me 0.4455269, you can round it maybe off to 4 decimal place, and you still 0.4455. So the point is, in this particular case, with the AIC, you've gotten 7964.75. At the same time, your CP is equal to the number of parameters that you have in your model. That is 6 when you're counting. I said you count from the equation. You're having 1, 2, 3, 4, 5 plus the intercept, that is 6. And then you've also gotten your adjusted R, which is 0.4455. That is for the case of the backward. Okay, like I mentioned, in R, you just need to type in the command and then direct it that, well, I want it either in backward, or I want it forward, or I want both, which is stepwise, which is the stepwise. So we are done with the backward selection. Let's see what happens in the forward selection. In your own free time, you try to read the comments, the notes that I've put. So, with the forward, remember, we first define the model with only what is the lower AIC. The lower AIC will determine after considering all the procedures. For now, in case it's one, you need to differentiate it from the others. That's when you determine that this is the lowest among the rest. So like I've mentioned so far, we've dealt with the backward, we've seen the AIC, we've gotten the R adjusted, and then we have the the CP. Those are three things that we are going to consider. Okay, now let's see, what about for the case of the forward? And we are also going to pick the AIC, we are going to pick the CP, we are going to pick the R adjusted. Okay, remember what we said with the forward, you only start a model without any regressor. So I state my LM, that is my linear model, my salary as a function of the intercept, no regressor, what we call the intercept only model. So in case I run this, okay, and then I can ask for, in case you ask for fit start, it is what I'm using as my object. When you run that particular line, you're going to only have the intercept, okay, as 11370.6. But in case you call for a summary and you run the summary of the fit start, what you're saying is that we are getting the estimate, we are getting the standard error, the t-value, and we are also told that our intercept is significant in this particular case. But like I mentioned, in case you run your intercept when it is significant, you have to make a decision on the rest of the other variables. Start adding in variables and see how do they influence the outcome variable. Okay, now after that, the next thing that I'm going to do, I come back again here in my step command. Okay, remember I'm using step. With the step, like we mentioned earlier, you can even ask R by using the hope command and see how it works. So from what you're seeing on the screen, you indicate the object first, which is this time around, it is my fit start, okay? And then now I want to indicate the direction that I want to use forward, okay? So you can run this particular step, and on that particular line, you can run it, okay? So now what happens in this particular case, because it is starting with only one variable, what you do to quicken your work, you come to this particular, because from here, I'm only seeing that salary is a function of one, the intercept model only, and it's also giving you the intercept. But now what you can do to quicken your work, you can come and put in this particular argument, and you indicate scope, the scope argument, and you tell it that formula fit all, implying that yes, I'm running, I'm considering a forward selection, but pick my variables. Remember we had fit all. Fit all, it was a regression that had all our variables. So I'm telling R, yes, my direction is forward, but start picking from all the variables that are left, which I defined in the fit all formula. So it's always important when you're dealing with forward selection to define your scope such that R is able to understand where to pick the other equations from, which we put in the fit all formula. So in case you run this particular line, what happens? Let's check and see. Like I said, R does it automatically, okay? The first one, in case you run the step, remember this is, our direction is forward this time around. And so it starts with an intercept only. And the AIC, the archaic information criteria, it's 8193.93, okay? And if you're seeing here, it has plus, implying that you have to keep adding, okay? So we are starting with 1, and then in case you add rank, okay, we add one variable at a time. In case you add rank, R is telling you that your AIC, this one, will reduce to 7998.9. Okay, so as we move on, we are going to see that in the second one, remember we are adding one at a time. We don't add everything at a go. That's why even if when you look at this particular, if you look at this particular side here, they start with the one that has got the highest correlation with the outcome is the rank. So it's what they started with. So when you move further, the next step now it's going to be how is salary a function of rank? So if this one is added, if you add rank now, your AIC reduces to that, to 7995.8. Then you rerun the model again. Now what you're going to do is, what about in case now it's still forward, but I've added the rank as a variable. I continue downwards. Now, in case now you run this equation, salary as a function of rank, it is telling you, we saw that the AIC reduced to 7998.98. That is what we had. So in case now you consider rank, okay? Now, if it is telling you now, you need to add another variable, discipline. If you add discipline, your AIC will reduce from 7998.9 to this one, 7966.2. Okay, and as you move further, because with the forward we are adding, then it is telling you now, where you see step, it implies that now we are moving on to another step. In the next model, we are adding discipline. And the moment we add discipline, our AIC becomes 7966.2. But when you look closely, as we are going to push, see, for it is saying that with the forward, do not add any other. We are seeing none. That in case you add more, it implies that you're going to distort the AIC and it will increase. Yet we are looking for the lowest, the one when as you add the independent variables, which one gives you the lowest AIC. So let's proceed and see. In case you add discipline, now you get salary as a function of rank plus discipline. Our AIC becomes 7966.19. It is the one here, only that it was now here, you can round it to 2 decimal places. So when you come to this particular step, after adding discipline, and when you look at the output, it's telling you that do not add anything again. That is what the forward selection is telling you. Do not go down. Otherwise, if you proceed, now you're going to distort the AIC. So in conclusion, for the forward selection, what forward selection is saying that no, the formula should be salary as a function of rank and at the same time a function of discipline. It is only considering among the different variables that we have, for it has considered rank and discipline and has dropped the rest when it comes to forward selection. So those are the two now so far the regression models that we have. It further gives you the correlation, the regression coefficients, the intercept, and then also basing on the rank at the same time the discipline. Okay, now let's move on further and see how we can extract the evaluation procedures that we want. Also, what I said, I can also put this particular line in an object which I'm calling forward AIC. You can change it to what you want. It has no problem. Remember, we've been discussing about what objects are. If I run this particular line, okay, it is the same thing. They are the same results that I'm going to come up with. I can as well come and then only run that. And it is giving me, for it automatically gives me the final model that I need, which is this one. So you can go in Word or wherever you're writing and state it out that my salary is a function of rank and discipline. So let's extract and see. What about, let's extract the AIC and then the CP and we see what happens, because in this particular case, there are only two variables they are considering. So I can use the extract AIC, okay, for my object. The moment I run this, sorry, I can run that particular line. Okay, let's continue. So that is just a by the way, something that got unstuck, so it shouldn't worry you. Now I want to run my AIC, this line here. So in case I run it, what happens, it is telling me that my the AIC for my forward regression model, it is 7966.186. It is the reason I told you we can create a table and we start comparing these results at the end of the day. And then my P is equal to, my P is 4. All right. And then I can get the coefficients, which I've already seen earlier about from the respective independent variables. And then I can also run my R adjusted, which is 0.4407. I can round it to 0.441. Okay, so now I am having my p-value as 4. I'm having my AIC for the forward as 7966.186, and then I'm having my adjusted as 0.441 in case I'm to take to, or I can say 0.4407. Okay, I can have it like that, or I can have 0.441. I keep that information aside. Now let's move on to stepwise, and later we'll compare the results and see. When we move on to stepwise selection, remember with the stepwise this time around, we are going to use still the step command, but we command R to use both. The direction is going to be both. That is how it is stated in R. So my command is step, is what I'm using. I put in my object, the fit start. Remember, the fit start is the one that had the intercept only model. Okay, the one for forward. We are starting with forward, intercept only model, but then we want to keep on adding and then minusing. You add and then minus. So I'm telling R the direction is both. Okay, then I pick this scope argument. Remember, I considered the fit start, which is an intercept only, but I'm telling R that I've got variables that I stored in the fit all object. So it should pick them and then consider and start either adding or minusing, starting with the forward selection of which I considered as fit start. This fit start was the one for forward. So I either add or in case R adds and it is less than 0.5, that variable, it will be retained. In case it adds and it is greater than 0.5, it will be dropped. But as the simulations go on and at a later point, the variable that was dropped becomes significant, it is then added back in the model. Okay, so I come and run this particular line. When I run this line, what happens? Let's see the output in the console. Okay, we are looking now at stepwise selection. Stepwise selection considers both the forward and then the backward. We start with the forward, we add a variable. If it is significant, if it's retained. The second variable is added. If it's not significant, it will be retained, and so on. That is the procedure. So when I start with summary as a function of one intercept model only, it is telling me that my AIC is 8193.92. Okay, this is my model, and it's telling me in case I now remember I'm starting to add now. In case I add rank, my AIC is going to reduce from 8193.93 up to this, up to 7998.9. Remember, we add one variable at a time. We run the regression mode again. We add another one, then we run the regression mode again. If it is not significant, R will automatically drop it. Let's continue. We are saying that now the next step, okay, until when we get to none. When you come to the next step, remember, if we put now rank in our model, our AIC reduces to 799.8.91. And when you look at this side here, R is saying that if you add discipline, okay, if you add discipline again on rank, then your AIC will further reduce from 7998.91 to 7966.2. All right, look critically. We are seeing a none here. It implies that those are the bounds. Don't skip further. Don't pick any. R is not going to give you more variables to add in the model, because if you pick more, the AIC will be distorted and it will instead increase. So the moment it gets to none, it will stop automatically and gives you the final model. So we have our AIC when we add discipline to 7966.19. So we cannot now go below the none, because it is saying in case you go further, the AIC will be distorted. So now your final model is here. We also, with the both, it is saying you only need rank and discipline in the data salaries as a function. You only need rank and discipline that influences salaries using the both. So if you've been very critical enough, even with the forward selection, it looked at only rank and discipline. Okay, let's continue further and see and extract out the AIC, the overall AIC. We check the R adjusted, and then we get the CP as well. So I come this particular line, extract AIC. The moment I run it, it is giving me 4 as my CP, the Maro CP, and then my AIC is 7966.186. So that is now for the stepwise. I can record it down. I record my CP. I don't need the coefficients for now. They are not important, but I need to see what about my R adjusted squared, which is 0.4407437. I can round it off to 0.441 or 0.4407, which is the same, similar to the one that was forward. So now we've got 3 regressions, okay? The one of forward, the one of backward, forward, and then both. So among these 3, we have one model that can easily fit our data best, which is appropriate to the data set that we have. It's the reason why I told you it is good that you create a table and then start comparing these results and see, depending on what we said, which one gives you the lowest AIC, which one, what about the CP, and then one which gives you the highest R adjusted squared. So basing on that, you can conclude and say, yes, as far as my data is concerned, I'm going to take the regression model either for the forward, for backward, or for both. I'm going to pause and ask in the chat, are we on the same page? Okay. Okay. Great. So what I'm going to do now, I'm going to stop sharing, and then I share a summary from what we've looked at. I'm going to share a summary of a Word document, and then we discuss together and see which among the 3 equations that we have, which one should we take up? Which one? Mm-hmm. Mm-hmm. Okay. So it's like just practical. Yeah, sorry, thank you. Okay, let's continue. There is a question. I talked about we can also use the CP, the Maro CP. This one is just equal to the number of parameters used in the model. And I said that in case you've got 4 variables, then your CP will be the 4 variables plus the intercept, making them 5. So a good model should have a CP that is equal to the number of parameters used in the model. Remember also an intercept itself is a parameter. Get the number of variables you add in the model, then you add the intercept. For example, when we considered the forward and then the backward, we saw that our CPs were all 4. How did we come up with the 4? Remember, we had variables, we had salary being influenced by rank, at the same time the discipline. So these are the 3 ones. And then we need to add the intercept, so making them 4. So a good intercept you should get a CP that is, a good model should give you a CP that is equal to the number of parameters being used in the model. That is the point there. And in all cases, it has been like that. So which is better, backward or forward? We are going to answer this and check from the discussion that we are going to have. We are going to discuss and see which is the best model we are going to pick. How is CP becoming 4? Yet if should be a probability. I think I've answered that. What is the negative AIC? Most of the time, we are looking at the smallest. The smallest AIC is what we consider. So in case you're comparing the archaic information criteria among the, whereby some of them are you have to choose among the ones, in case there are 4 of them, the lowest is the one that you do pick. Anyway, let's consider this. I only considered AIC, the R adjusted squared, and then the CP. Let me ask in the chat, are you seeing the document I've shared, the Word document? Have you seen the Word document? Okay, great. Now let's discuss. Now it's you who's going to tell me the answer that we are going to pick up. Remember, after choosing the best model, the next thing is that the appropriate model, not the best, but what is appropriate for your data is depending on the data set that you're using. After that, what we shall do, we need to move on and check whether the assumptions of them, it's a model we'll take. Among the 3, we have to choose one model. And then thereafter, we need to check whether the regression assumptions are not violated. And the moment after checking that, we do the analysis, which analysis you already looked at. So now, this is the table I created, I was talking about. I've got my criteria, the ones I'm considering. I've got the backward regression, the forward, and then the one of both implying that I considered the backward and then the forward. So with this model here, this is the first one. Okay, let me write and say, oops, sorry. Let me say, yes. If I call this model 1, okay, that is my backward, and I call this model 2, and then I come here and I call this one model 3. In other words, we've got 3 regression models, but we cannot use the 3 of them. We need to choose the one that fits our data very well. When you look at the AIC, for model 1, the backward, we had 7964.75. When you look at the forward, we had 7966.186. The same applies for the case of both, where we had backward and forward. But remember, we need to choose a model that has got the smallest AIC. So basing on these 3 models, critically, you can look and say, among the values that I have, I can tell which one has the smallest AIC. When we come to the R squared adjusted, you pick the one with the biggest value. So the first model has 0.4455. The second one has 0.441. The same applies to the third model. When we come to the CP, The first one had 6, which is okay, because we had 5 variables plus 1. We got the intercept plus the intercept, making them 6. Here in the second model, we had 3 variables, the salary, the discipline, and then the rank. Those are 3 plus the intercept, giving us 4. The same applies to the last one. So it is from here you decide out and say that, okay, basing on my table, I'm going to choose this model will be the one that will fit my data well. So I'm going to ask in the chat, from the table, from the results that you have, which one should we opt for that will quickly fit our data well? Yes, wonderful. And I'm so glad that all the answers, I'm seeing model 1 backward, model 1, 1, 1, 1. I think everything, model 1 is better. Wonderful. And even if I'm the one, I'll choose model 1 because it has got the smallest AIC, it has got the highest adjusted R squared, and the appropriate, and it has the CP. All these reasons, all these criteria help us understand what model we need to pick. Okay, great. I think that is what I wanted to share with on model building. So the same criteria applies to the different data sets that you have or the data that you've collected. In case you want to do regression analysis, you can as well first go ahead and do variable selection and get to know what variables quickly that are significant to your response variables. And so you go ahead and pick that. So that was the first objective. Okay, let me ask in the chat and see, does it? Yes, it does hold. Well, there are some others. For example, Nyango is asking about the mean square error. So now I'm going to give you just a small homework using this same model. Then you can go ahead and check for the MSC. Okay, we want to check still the one that will give us the smallest mean square error, and then we can also check for press. Okay, the one that will have the smallest value for press, it will be the best model to give us the great predictability. But most of the time in literature, they consider these procedures, but you can as well also add them on, and you will see that even if you calculate the MSC, the model 1 will be the best, and when you get the press, it will be model 1. You can check that as your homework, and then you can share with me tomorrow. That marks that particular bit, and you can apply them now to the rest of your data set. So, okay. Okay, can somebody post a reason, the different reasons in the chat why we chose model 1? Can somebody post some reasons? Okay, the lowest AIC, IA small, high adjusted and highest CP, great, because AIC is small, high RS, yes. I think all those are the reasons that we're based on why we've concluded that model 1 will be the best as far as it will be the appropriate for the model that we are considering. Thank you so much. I think the person who was asking, that one has been clearly answered. Okay, that marks that part. Then the other part that we are going to look at, if you allow me, I want to move on to, let me share, and then the next bit, if it is okay, I want to move on to analysis of categorical data. And then if time allows, we still do it in R, and that will be super nice. Okay, let me ask in the chat. Can I continue? We go on. Okay. So let's also, no lunch. You'll have lunch after. We have 20 minutes to end. And they're asking about the registration form. Kindly post. No lunch, we'll have lunch after. Let's look at also, in case you have questions, kindly post them in the Q&A. Thomas and Susan are just excited to answer all your questions. So post them there and they'll be glad to answer. So let's now move on to the last bit on analysis of categorical data. Remember, as we've been echoing it out, it is always important to understand the nature of your data set, whether it is experimental data, whether it is a survey, everything starts with a data set. And then from your data set, it comes back to what kind of analysis do you want to do. A computer, it's a garbage. Whatever you feed in, it will give you result. But getting the appropriate statistical method that you need to have is very important. When do we and how do we analyze categorical data? Remember, in R, we've been using the as factor command, because most of the time when you're feeding in data that is categorical, R reads it as a character. So you need to tell it that no, it is categorical in nature. So let's proceed and see what happens. So because in case your dependent variable is categorical in nature, okay? For example, maybe being admitted at the university, in case you've got two attributes or two levels, either somebody is admitted or not admitted, and it is your dependent variable, then it implies that we are going to use a chi-square test. We use a chi-square test when we want to analyze categorical data. Okay, sometimes you can have more than two levels, and then we see how do we go about that. For example, maybe you're looking at how different factors influence the weight among children, and you have categorized your weight into 3 levels. All right, maybe you have poor, fair, and then maybe the other one is good. Okay, how do you go about analyzing such kind of data? So we use a chi-square test to test the dependency between 2 categorical variables. However, it can be more than 2. And under the chi-square test, we need to ask ourselves what are the different observed proportions of frequencies, and then the expected proportions. And most of the time, everything emanates from what we call a table, a contingency table, or you can call it a cross-tabulation. And this is a kind of a table that puts data in form of counts. Okay, the data usually is in form of counts, and so they are crossed in such a way that you're trying to see the relationship between an independent variable and a dependent variable. So in this particular case, with just an example that I'm showing here, I had color, the relationship between color and then the price. Among the colors, we had black, blue, and then gold. Okay, and then the price, which is the dependent variable, it's either high or low. So what is happening when you use the table in R? In R, we use a table to get a contingent. The table command can give us a cross-tabulation table or a contingency table, and you are able to tell the different frequencies or the counts that follow under each particular category. And so they usually compute the total rows and then the column. So here we can see that with the black, okay, the color, so there are 15 of high price, and then there are 21 of low price. The ones that are blue, there are 16 of high price, and then 22 that of low price, and so on. Still in R, you can be able to compute the totals. We call them the total margins, both at the column wise and also row wise. So let's get to understand more about a chi-square test. Okay, you find that usually, where is it applicable, commonly applied? Number one, when you want to test the independency of association between 2 variables, you can also use it in case you want to test for equality of proportions in more than two populations. And then you can also use it in case you want to test for the goodness of fit. So but the point is that you need to understand at what extent do the observed and then the expected frequencies differ. We're going to go into more details to understand what these things mean. So when you're analyzing categorical data, you need to first understand that what do they refer to? We are talking about the data is classified into categories so that you get frequency counts in each category. Like the example we saw earlier, that the blue has this amount, this frequency when the price is high, and then this frequency when the price is low. And it's also desirable to know whether the classification of an individual according to one system, that is one variable, is independent of the other, that is the dependent variable. Okay, so for example, in case you want to check there is independence of species and infection, this so we want to see is whether there is an association or there is no association. In other words, does the infection rate depend on the kind of the species or it doesn't? So in other words, we still create hypotheses. We can create hypotheses, the null, and then the alternative, and check whether there is an association or whether there is dependency or there is no dependency. Remember, chi-square is used to test for independency. Okay, let's take this example. A bunch of 1,500 wooden steps were divided at random into 3 groups of 500 each. Each group received different termite repellent treatment. The treated sticks were driven in the ground at locations selected at random. 2 years later, the stakes were examined for termites and the data is summarized below. So this is what we have. We are having different groups, okay? And then we are having the 3 groups and then the termites. We have those that were attacked by the termites and then where they are not attached by the termites. So in group 1, the count is 193. That was attached by termites. In group 2, we have 148. In group 3, we have 210. These subtotals you're seeing, they're just summing up all the 3 groups and we are having that. The same applies to not attached by the termites in group 1, group 2, and group 3. Okay, and there's a question that which variable should be in the row and then in the column. In the row, we put the dependent variable, and in the column, we put the independent variable. That is how it works with the categorical analysis. Okay, so we are seeing the frequency counts, they have been classified according to the groupings, and this particular table, it's what we call a cross-tabulated table or a contingency table. And this particular case, it is a 2 by 3. We've got 2 rows because our dependent variable is attacked or not attacked. And then we've got 3 columns, which are the groupings that we are considering. So it is a 2 by 3 contingency table. Let me ask in the chat, are we still on the same page? Can I continue? Okay. All right. No. Is it? Depending on the analysis you want to do. Okay, let's move on. In case you want to test for independency, I'm using the general terms. So you can, step 1, if you're putting the hypothesis, by the way, your conclusion will always depend on how you've set up your null hypothesis, all right? So in case I consider H0 and I say that 2 classifications are independent, That is, and then the alternative is that the two classifications are not independent. So it depends on how have you set up your hypothesis. And then step number 2, we need to calculate the expected values. What you see in the contingency table, those are the observed values. But now, how do we calculate expected values? The formula, we get the row totals times the column total divided by the grand total. In case we go back shortly, these are the row totals for the first one, then if for the second one, and then this is our grand total. This is the total for group 3. This is the total, the subtotal for group 3. This is the total for group 2, and then and so on. Then the grand total is 1,500. However, when you get to a software, it is done automatically. So you don't need to worry. All you need to do is to fit in the right command, and then you will get the result. So how do you calculate the expected frequency? This is what I've just mentioned. That how do you get it? You multiply the product of the marginal probabilities by n, and then the total number of observations. The row I total times the column j total divided by the total number of observations. Okay, and then the other step that we need to calculate the diversions for each cell of the table. That is, having gotten the expected frequency. So how do we get the diversion for each cell? We get the observed frequency minus the expected frequency. Then the last bit, we compute the chi-square. The formula for chi-square is, let me get to the next slide. I think it's clearly, which is our test statistics. They're telling us here, this is our test statistics in case the formula for chi-square test. These are the observed values if you're considering, depending on the groups that you have, I and J. I is reading the rows, and then J is reading the columns, okay? The first row, first column, depending on the cell where you are. And then you minus the expected values. We've seen how to calculate them, I and J, then divide by the expected value of E and J. We get the difference in divergence, which I've just talked about, and then we square it. So what R will do, or the computer will do, it will sum, depending on the cell that you've started in, that we are summing from I equal to 1 to R. This for the case of the rows, and then for the case of the columns. So it adds everything together. And then, but with the chi-square test, it is with the 1 degrees of freedom that are we going to consider. We have the rows, degrees of freedom with chi-square test is equal to R bracket R minus 1, then times C minus 1. R, those are the number of columns, and then C, those are the number of rows. You minus 1, you multiply it, and then you come up with the degrees of freedom. Remember, we've also gotten chi-square tables, which you can consider. So this is what I've just talked about. Like in the previous example, we had 2 columns, so it is 2 minus 1, and then we had three columns. So it is 3 minus 1. When you multiply, you come up with 2 degrees of freedom. And then you can, in case you're considering the chi-square tables, which we call the critical value you read from the tables. In this particular case, it is from the table, it is 5.99 at 2 degrees of freedom. Okay, but from the calculated one, in case we use this one, if we calculate, we come up with 17.66 on 2 degrees of freedom. Okay, so still what we do now, we compare, taking the level of significance as 0.05. We are still determining with a tabulated value at 2 degrees of freedom, it is 5.99. And then the calculated one is 17.66. So the point is, when do we reject? Do we, considering your narrow hypothesis, now you need to come up with a conclusion. So what is going to happen is that, remember how you set your narrow hypothesis. Your narrow hypothesis was, if I remember well, it was 2 classifications are independent, then 2 classifications are not independent. So we are going to come and say that if the calculated value is greater than the critical value, or the value that you read from the table, then it implies that you reject H naught, and the reverse is true. Always note that when they tabulated all the critical value, is, so I can take the opposite. When it is less than the calculated, then we reject H naught. Okay, so in general, let's look at this. In general, in case I'm considering my H naught for no independency, and then my H1, there is independency. This is what we've been looking at even in regression analysis, checking if there is a relationship, but now for the case of categorical data. So depending on the level of significance, you've said whether it's 5% or 1%, when they calculate, when the table value, the value that you read from the chi-square table, from the statistical tables, okay? When you read the chi-square table, with that value that I'm considering the critical value, the moment it's less than the calculated, you've seen how we can calculate the chi-square using the test statistics. Then what happens in that particular case? You reject H naught. Otherwise, you do not reject. You act, you take on the alternative. So that is the criteria that we are going to use to go through. So, and then later we'll move on to R and see what happens. Let's take another example. I extracted it from a textbook. So what we are having in this particular case, data was collected. It's a descriptive data, whereby you've got offenses that were committed in a certain city. At the same time, the area. These are offenses. We had burglary, robbery, car theft. And they're telling us that in area A, which I'm calling the city, the offense that was committed under burglary, we had 30, then robbery was 19, car theft was 6. So the total is 55 in area A. When you come to area B, the offense of burglary was 12, robbery was 23. These are just counts, car theft was 14. Then you get the column, the row total. The same when you come to area C, we had 8 for burglary, we had 18 for robbery, car theft it was 20. So these are the totals. The totals here, you just add the total offense for the burglary, the total for robbery, and then the car theft is 40. So these are the totals we have. And the overall total of offenses that were committed, that were there, it is 150. So the question is, in 3 cities, so this is, we are trying to see whether there is a relationship between the number of offenses committed in relation to the city where those offenses were committed. So in an area, in 3 areas of a city, a record has been kept of a number of burglaries, robberies, and car theft which take place in a year. The total number of offenses was 150, and were divided into various categories as shown in the contingency table. Okay, so what you're seeing in these cells, it's what we call, these are the observed frequency. What we are seeing here, 30, 19, and 6, okay? And so we need to move on and understand how do we compute the observed frequency, how do we compute the expected frequency, because what we are having here are the observed frequency. So let's now state the hypothesis. The hypothesis, the null is no association between offenses and the area of the city. And then the alternative association there is an association between offenses and the area of the city. So it is always important to, at the back of your mind, to understand what the computer does. So this is what has been computed with the observed values, or the observed frequencies, the ones that we had earlier there, and then the expected frequency. How do we compute the expected frequency? I've already shown that we use this formula, so we can, but in R, it is already inbuilt there. And then we get our chi-square, the formula that we use, this one here. It's there for the test. That's what we are going to get. So we'll get the total at the end of the day. So we are getting for each block, okay? For each block, it's being calculated, but later at the end of the day, they're going to sum up this, that, you add everything up. So this is what we are having. So overall, using the equation that I showed you, when you add all the chi-squares for each box, in this particular case, I mean this value here, then this other one, even here, you continue, you add up to 4.82. So the calculated value is 23.13. And how are we going to get our degrees of freedom? Remember, basing on what we are having on this particular example, we've got 3 rows and we've got 3 columns. So the columns are equal to the rows. So what is going to happen from our formula, degrees of freedom is equal to R minus 1, then bracket times C minus 1. So we are coming up with 3 degrees of freedom. So in case we are considering a significancy level of 0.05%, what happened is that when you read from the table, the critical value, when you're considering 4 degrees of freedom and considering the level of significancy at 0.05, the chi-square value we are getting is 9.488. So the point is, are we going to reject the null, or we are going to accept it? Are we going to conclude that there is an association or there is an association? What criteria did I mention? That in case the table value is less than the calculated, we reject the null hypothesis. The null is that there is no association. The alternative is there is an association. And we clearly see that the table value or the critical value is less than the calculated value. That is 9.488 is less than 23.13. So we are going to reject the null and then opt in for the alternative. Okay, now what about in case you take it as 1% significancy level, that is 0.01. Still, when you read from the table, the critical value is changing to 13.28. Again, this value is less than the calculated value at 23.13. So still, in this case, we are going to reject H naught and we'll go in for the alternative. So we'll conclude and say that there is a strong evidence of association between the number of offenses and the city where they are committed. Let me ask in the chat, are we on the same page? Okay. It's already past 2. Okay, let me discuss this part and then maybe I will do the practicals tomorrow because I'm saying we already passed. Huh? What are they saying? Okay. Okay, let me discuss this part and then we stop. Is it okay? Or you're tired? There are just few slides remaining. E is the expected, those expected frequency. So tired. So what can we do? Okay. Yeah? Continue tomorrow. Okay, so I'm going to stop here, but there is an exercise. So please try to work out this and then you'll share with us tomorrow. It is within the slides. Check and see whether we want to check if there is there's an association between the shape and color of the seed. If there isn't, then you'll share with us. Okay, since everyone is saying we are tired, I'll start from there tomorrow and then we'll continue. Thank you so much. I'm glad that you persisted. So we'll do the practicals tomorrow. Yes, we will. We'll finish and then do the practicals tomorrow. Thank you and bye-bye. Now, me, I don't want to continue when they are not understanding. Okay, we'll resume tomorrow. Bye-bye.